The most dangerous thing about traveling to Proxima Centauri is not the void. It is not even the radiation. It is the fact that the moment you leave Earth, your own biology turns against you. You would leave Earth as a human being. Whether you would arrive as one is genuinely uncertain, and that is not a philosophical question. That is a medical one. If you are the kind of person who wants to understand the universe, make sure to give this video a like. Now let's get started. Here is something that will quietly ruin your sense of scale. Proxima Centauri is so close that astronomers consider it practically next door. And yet, if you pointed the fastest spacecraft ever built directly at it and hit launch, the Roman Empire would rise and fall before you were even halfway there. That is how broken our intuition about space actually is. But let's say we solve that. Let's say a future generation cracks the propulsion problem and builds a ship that can cross 4.24 light-years in 20 years. That is actually on the table. Breakthrough Starshot, backed by Stephen Hawking and Yuri Milner, is a real proposal to do almost exactly that with small unmanned probes using laser propulsion. 20 years. Sounds almost manageable, right? Here is what nobody is talking about. The engineering problem is hard, but it might actually be the easy part. Because the question that keeps serious researchers up at night is not how do we build a ship fast enough. It is this: what would 20 years in interstellar space do to the human beings inside it? Not to the ship, to the people. And if that question already has you feeling that beautiful tension between curiosity and dread, then I need to point you toward the video exploring why interstellar travel gets more terrifying the further you go on the card above. It picks up exactly where this one leaves off. What happens when you push past Proxima Centauri, what the universe starts doing to a ship traveling at a significant fraction of the speed of light, and why the further you go, the more the rules of reality seem to break beneath you. The link is in the description and pinned on the comment. Here is what we actually know about what long-duration spaceflight does to the human body. In 2019, NASA published the results of what is now called the Twin Study in the journal Science. It is one of the most remarkable human biology experiments ever conducted. Astronaut Scott Kelly spent 340 days, almost 1 full year, aboard the International Space Station. His identical twin brother, Mark Kelly, stayed on Earth. Same genes, same upbringing, same baseline biology. Different environments. The results were extraordinary, and not in a reassuring way. After 340 days in space, Scott Kelly's gene expression had changed significantly. We are not talking about mutations. We are talking about which genes were active and which were silent. In space, thousands of genes that were previously quiet switched on. Thousands of others that had been active switched off. His immune system went into an unusual state of heightened alert. His gut microbiome, the community of trillions of microorganisms that live in your digestive system and are deeply connected to your immune function, your mood, and your cognitive performance, shifted measurably. His carotid arteries, the major vessels carrying blood to the brain, showed thickening of their walls, a marker of cardiovascular stress. His telomeres, the protective end caps on his chromosomes that are associated with aging and cellular health, behaved in unexpected and unstable ways. And then there was his vision, Scott Kelly, along with a significant percentage of astronauts who have spent extended time aboard the International Space Station, experienced a condition now called spaceflight-associated neuroocular syndrome, SANS for short. In microgravity, bodily fluids shift toward the head. Over weeks and months, this increased fluid pressure pushes against the optic nerve, reshaping the eye itself and degrading vision. In some astronauts, these changes have been long-lasting. We do not yet fully understand why some people are more susceptible than others, and we do not yet have a reliable countermeasure. Now here is the critical detail. Scott Kelly spent 340 days in low Earth orbit. He was still inside, or partially inside, Earth's protective magnetic field, which shields us from much of the dangerous radiation that fills space. He had regular resupply missions bringing fresh food, equipment, and medicine. If something had gone catastrophically wrong, he could have been back on the ground in a matter of hours. A crew traveling to Proxima Centauri would have none of that. They would spend 20 to 25 years in deep interstellar space. Beyond the heliosphere, the bubble of charged particles and magnetic fields that the Sun generates, which provides some additional shielding from cosmic radiation, beyond any resupply, beyond any evacuation. And in a communication situation that is, when you truly think about it, one of the most isolating scenarios in the history of our species, radio signals travel at the speed of light. So a message sent from the ship to Earth would take 4.24 years to arrive. A response from Earth would take another 4.24 years to get back. That means a single round-trip conversation, one question and one answer, takes 8.48 years. Think about what that means in a medical emergency. If something goes wrong on the ship in year 7 of the mission and the crew immediately sends a distress signal, Earth does not even know about the emergency until year 11. The earliest any medical advice could possibly reach the crew is year 15. By then, 8 years have passed since the emergency began. Whatever happened, it has either been handled internally or it has not been handled at all. This is not a problem you solve with better technology alone. This is a problem that demands a different kind of human. A human who can make life or death decisions in total isolation, with no expert backup, no second opinion, and no emotional support from anyone outside those ship walls. A human whose biology is stable enough to survive 2 decades in an environment evolution never prepared us for. And that word, evolution, is exactly where we are heading next. Because here is the thing about radiation. The cosmic radiation environment of interstellar space is not just dangerous, it is something that life on Earth has never, in 3.8 billion years of biological history, had to face directly. Our DNA has repair mechanisms, our cells know how to respond to damage up to a point. But the high-energy galactic cosmic rays that stream through interstellar space at nearly the speed of light, they punch through metal, they punch through shielding, and what they do to the human brain, specifically to the neurons responsible for memory, reasoning, and emotional regulation, is something that should make every aspiring astronaut pause. Stay with me, because this is where it stops being an engineering problem and starts being an existential one. Let's talk about your brain for a moment. Right now, inside your skull, there are approximately 86 billion neurons, individual nerve cells, each one connected to thousands of others through a web of synaptic links so complex that some neuroscientists genuinely believe it rivals the observable universe in its intricacy. Every thought you have ever had, every memory you carry, every fear, every moment of joy, every decision that has ever defined who you are, all of it lives inside that roughly 1.4 kilogram structure sitting between your ears. Now imagine something punching through it. Not once, not occasionally, constantly, for 20 years. That is not a metaphor. That is the literal reality of what galactic cosmic rays would do to the crew of any interstellar vessel we could conceivably build today. Let me explain what galactic cosmic rays actually are, because the name makes them sound almost poetic, like something you would name a band or a perfume. They are anything but. Galactic cosmic rays, GCRs, are subatomic particles, mostly protons and the nuclei of heavier elements like iron and silicon, that have been accelerated to nearly the speed of light by violent astrophysical events, supernovae, pulsar wind nebulae, perhaps even the shockwaves of colliding galaxies. They travel across the galaxy in every direction, and they carry energies so extreme that our most powerful particle accelerators on Earth cannot replicate them. When one of these particles strikes matter, including human tissue, it does not simply pass through cleanly. It creates a cascading shower of secondary particles, tearing through molecular bonds, snapping strands of DNA, and leaving a trail of ionized destruction at the cellular level. On Earth, we are protected from most of this by two things: our planet's magnetic field and the thick column of atmosphere above our heads, roughly 10 meters of water-equivalent shielding, which is extraordinary. On the International Space Station, astronauts receive doses of radiation that are already roughly 10 times higher than what a person on the ground experiences, but the station still sits within Earth's magnetic umbrella for most of its orbit. In deep interstellar space, both of those shields vanish entirely. Now, the question scientists have been working urgently to answer is this: what does prolonged, unavoidable exposure to GCRs actually do to the brain? And the answers coming back from research centers around the world are, to put it plainly, alarming. Here is where I need to take you to a place most science videos never go: a particle accelerator facility in Upton, New York, called Brookhaven National Laboratory. For years, NASA has funded research there specifically designed to simulate the cosmic radiation environment of deep space and study what it does to living tissue. And some of the findings published in the last decade have genuinely shifted how seriously the scientific community takes the neurological threat of interstellar travel. In a study published in 2015 in the journal Science Advances, researcher Charles Limoli and his team at the University of California, Irvine, exposed mice to charged particle radiation at the levels expected in deep space. The results were striking. The irradiated mice showed significant impairments in memory, learning, and what researchers call executive function, the ability to plan, make decisions, and adapt to new situations. These are not peripheral cognitive skills. These are the core functions that define sophisticated human thought. But it was not just what the mice could not do, it was why they could not do it. Imaging of the irradiated brains showed measurable reductions in the density of dendritic spines, the tiny branch-like projections on neurons where synaptic connections are made. Fewer dendritic spines means fewer connections. Fewer connections means a less integrated, less capable brain. The neural architecture was literally being dismantled from the inside. A follow-up study published in 2017 went further. This time, the researchers found that cosmic radiation did not just reduce the number of synaptic connections, it also triggered a sustained state of neuroinflammation. The brain's immune cells, called microglia, were persistently activated, behaving as though the brain were under constant attack, because in a sense it was. And chronic neuroinflammation is associated with a range of serious conditions here on Earth, including accelerated cognitive decline, depression, and increased risk of neurodegenerative disease. Then came another layer. A 2018 study, also from Limoli's lab, found that cosmic radiation appeared to interfere with the functioning of the prefrontal cortex specifically. The prefrontal cortex is the region of your brain most responsible for impulse control, emotional regulation, long-term planning, and complex social behavior. It is in many ways the seat of what we consider our most distinctly human cognitive capabilities. Now think about what that means in context. You have a crew of human beings, 6 or 8 or 12 people, sealed inside a spacecraft smaller than a luxury apartment, traveling through the void for 2 decades. Their relationships with each other are the only social world they will know for the foreseeable future. The psychological pressures of that isolation, we will get to those in detail in a later section, are already immense. Now add to that a radiation environment that is quietly, progressively degrading the very brain systems responsible for managing stress, regulating emotion, and making sound decisions, this is not a background concern. This is a mission-critical threat that we do not yet know how to solve. And here is what makes it even more sobering. We cannot simply shield our way out of this problem, at least not with any material we currently know how to produce at scale. The physics of GCR shielding is deeply counterintuitive, with lower energy radiation like X-rays or gamma rays. Adding more dense shielding material generally means better protection. Lead walls, thick aluminum hulls, these work well against that kind of radiation. But high-energy galactic cosmic rays behave differently. When a high-energy particle hits a dense material like steel or lead, it undergoes what is called nuclear fragmentation. It smashes into atoms of the shielding material and creates a spray of secondary particles. In some scenarios, the secondary radiation coming out of the far side of thick metal shielding is actually more biologically damaging than the original particle that struck it. Denser is not always safer. The materials that work best against GCRs, materials with lots of hydrogen atoms, which are small and light and effective at absorbing high-energy impacts, include things like polyethylene, water, and even food. Some researchers have seriously proposed designing spacecraft interiors with the food and water stores built into the walls as a radiation buffer, a practical and genuinely creative solution, though it comes with its own engineering complications. But even the best passive shielding we can design today would only reduce GCR exposure, not eliminate it. Over a 20-year mission, the accumulated dose would still be substantial. One 2014 analysis estimated that a crew on a long-duration deep space mission would receive total radiation doses potentially in the range of 1 full gray, a unit of absorbed radiation or higher, depending on solar weather conditions. For context, a dose of around 4 grays delivered to the whole body over a short period would be lethal to approximately 50% of people without medical treatment. Chronic exposure spread over years is a different biological situation, but the cumulative DNA damage, and especially the neurological impact, remains deeply concerning. And there is a wild card that complicates all of this further. Solar particle events. The Sun periodically releases enormous eruptions of charged particles, solar flares and coronal mass ejections. Inside our solar system, these events are dangerous but somewhat predictable, and we have monitoring systems to give astronauts advance warning. In interstellar space, far from any monitoring infrastructure, a large solar particle event could deliver a massive radiation dose in a matter of hours, with virtually no warning and no shelter available beyond whatever the ship itself provides. So the radiation environment of interstellar space is not a single steady threat. It is a layered, complex, and partially unpredictable assault on human biology, one that we are only beginning to understand in its full depth. Now here is where I want to shift perspective, because everything I have just described, the dendritic pruning, the neuroinflammation, the prefrontal cortex degradation, is being studied and documented not to scare us into giving up. Quite the opposite. It is being documented because serious scientists and space agencies believe that if we understand the problem deeply enough, we can eventually find solutions, and some of the proposed solutions are extraordinary. One avenue being actively explored is pharmacological. The idea that drugs or targeted biological therapies might be able to reduce neuroinflammation, stimulate the repair of synaptic connections, or protect neurons from radiation damage in real time. Antioxidant compounds, anti-inflammatory agents, even certain drugs already used in oncology are being examined for their potential as radiation countermeasures. Research published in 2023 by Limoli's team showed that some antioxidant treatments administered to rodents before and during radiation exposure produced measurable improvements in cognitive outcomes. It is early-stage science, but it is a genuine signal, Another avenue, and this one gets philosophically vertiginous very quickly, involves the possibility of genetic modification. If we could identify the specific genetic variants that make some individuals more resilient to radiation damage, and there is already evidence that such variation exists in human populations, could we select or even engineer future crew members for enhanced biological resilience? This is not purely theoretical. The CRISPR gene editing revolution has made targeted modification of human DNA genuinely feasible. The ethical questions it raises are enormous. But so is the problem it is trying to solve, and then there is an idea that is even more radical. What if the answer is not to protect the human brain from radiation, but to fundamentally change what it means to be human for the duration of the journey? Some researchers, and I want to be clear that this sits firmly in the speculative end of the scientific spectrum, though it is discussed in serious academic literature, have proposed the concept of induced hibernation, or torpor. The idea is borrowed from what certain mammals do in winter, dramatically reducing metabolic activity, lowering body temperature, slowing breathing and heart rate to a fraction of their normal levels. In this state, cells consume almost nothing. Damage accumulates far more slowly. Time, from the perspective of the hibernating organism, effectively compresses. Could humans be induced into a prolonged torpor-like state for the duration of an interstellar cruise? The answer, as of right now, is that we genuinely do not know. NASA has funded early-stage research into the concept, a project called Torpor-Inducing Transfer Habitat, which explored whether cooling and sedating human subjects could achieve something metabolically similar to animal hibernation. Results have been limited, and the science is far from mature, but it remains an active area of inquiry precisely because the payoff, if achievable, would be so transformative. But here is the thing I keep coming back to. Here is the thought that surfaces every time I go deep into this research. Even if we solve the radiation problem, even if some combination of pharmacology, genetics, shielding, and hibernation technology brings the neurological risks to a manageable level, we still have not addressed what might be the deepest challenge of all, the mind, not the biology of the brain, the mind, the subjective, inner, lived experience of being a conscious human being locked inside a metal cylinder, surrounded by 4 of the most hostile light years in the known universe for 2 decades, without the sky, without seasons, without the feeling of wind, or the smell of earth after rain, or the sight of a horizon, without anyone outside those walls who can reach you in any meaningful time frame. What does that do to a person? What does it do to a group of people? What happens to human identity, to the sense of self, of purpose, of meaning, when the entire context that normally anchors those things is stripped away, possibly forever? When the Voyager 1 probe crossed the heliopause, the outer boundary of the Sun's influence, in 2012, it became the first human-made object to enter interstellar space. Scientists detected the change through shifts in the plasma environment around the probe. The boundary was real and measurable. The distance Voyager 1 has traveled since its launch in 1977, nearly 50 years of continuous flight, is approximately 23.3 billion kilometers. Proxima Centauri is 40 trillion kilometers away. Voyager 1 has covered less than 0.1% of that distance. We are, as a civilization, at the very base of this mountain. We have not even found the first trail, and yet we are already asking the right questions. We are already peering into the biology, the neuroscience, the psychology of what it would take. That, to me, is one of the most extraordinary things our species has ever done. There is a moment that several Antarctic winter-over researchers have described independently in interviews, in journals, in psychological evaluations conducted after their return. It happens somewhere around the 3rd or 4th month of isolation, deep in the polar winter, when the last supply plane has long since departed and the next one is still months away. The sun has not risen in weeks. The temperature outside is cold enough to kill an unprotected person in minutes. And something inside the mind, something quiet and fundamental, begins to shift. Some describe it as a kind of flattening. Emotions that were once sharp and immediate begin to feel distant, like signals coming from far away. Motivation drains. The future, which had always felt like a direction, a place you were moving toward, starts to feel abstract, almost fictional. Time loses its texture. Days blur into one another. And the people around you, the small handful of colleagues you share your isolated world with, begin to feel simultaneously like your lifeline and the source of your deepest irritation. This phenomenon has a name. Researchers call it the third quarter phenomenon, a well-documented pattern of psychological deterioration that tends to peak roughly 3/4 of the way through an isolated, confined mission. It has been observed in Antarctic crews, in submarine deployments, in long-duration spaceflight simulations. It is not a sign of weakness or poor preparation. It is a predictable, measurable response of the human psychological system to an environment it was never designed to inhabit. Now take that phenomenon and stretch it across 20 years. Let me introduce you to Mars 500. In 2010, the European Space Agency and Russia's Institute of Biomedical Problems launched one of the most ambitious psychological experiments in the history of human spaceflight preparation. 6 volunteers, 3 Russians, 1 Chinese, 1 Frenchman, 1 Italian Colombian, were sealed inside a series of interconnected metal modules in Moscow. The facility was designed to simulate, as closely as possible, the experience of a crewed mission to Mars. The confined space, the communication delay with the outside world, the limited resources, the absence of natural light, the total social isolation from everyone outside those walls. They stayed inside for 520 days. No natural sunlight, no fresh air, no spontaneous human contact with anyone beyond their 5 crewmates. Every communication with the outside world was subject to an artificial time delay, simulating the actual signal lag of a Mars mission. 520 days. That is roughly 1 year and 5 months. The psychological findings were illuminating in the most uncomfortable way. By the latter stages of the simulation, several crew members had developed significant disruptions to their circadian rhythms, their internal biological clocks, which regulate sleep, hormone release, metabolism, and mood. Without natural light cues, the brain loses one of its most fundamental anchors to time and biological regularity. Some crew members began sleeping at increasingly irregular hours. Activity levels dropped substantially across the group. Researchers monitoring the crew observed what they described as a kind of hibernation response, not the medically induced torpor we discussed in Part 2, but a spontaneous psychological and physical withdrawal from activity and engagement. Perhaps most striking was what happened to the crew's relationship with time. In structured interviews conducted after the simulation ended, several participants described a profound distortion of temporal perception. Weeks had felt like days, months had collapsed. The experience of time, which we normally rely on to structure meaning, to feel progress, to maintain a sense of narrative in our own lives, had become unreliable. And when time becomes unreliable, so does identity, because who we are is, in a very deep sense, a story we tell about ourselves across time. Disrupt the experience of time, and you disrupt the story. Now here is the critical difference between Mars 500 and an actual interstellar mission, and it is a difference that should stop you in your tracks. The volunteers in Moscow knew they could leave. Not easily, not without consequences for the study, but the door, metaphorically and literally, existed. The outside world was still there, unchanged, waiting. Their families were a phone call away, even if they were not allowed to make those calls freely. Earth was at most a few meters of metal away. On a ship bound for Proxima Centauri, there is no door, there is no outside world waiting unchanged. There is no family a phone call away, because any message sent takes 4.24 years to arrive and another 4.24 years for a reply to return. By the time a crew member could receive a response to a message sent from the midpoint of a 20-year journey, the person who sent it would be a decade older. Parents who were alive at launch might be gone. Children born just before departure would be approaching adulthood, having grown up in every practical sense without a parent. This is a category of psychological reality that humanity has genuinely never faced before. We have stories of long sea voyages, of explorers who disappeared into unknown continents for years. But even the most isolated historical adventurers, Antarctic expeditions, transoceanic sailors, existed in a world where return was, at least in principle, possible within a human timeframe, where the people they left behind were aging at the same rate they were, where the civilization they came from was still recognizably their civilization. An interstellar crew operating under even the most optimistic propulsion scenarios would leave a civilization and return, if they returned at all, to one that is 20 to 50 years older, one that has changed in ways impossible to predict. Technology, culture, politics, language, all of it shifting in their absence, while they exist in a kind of temporal suspension, connected to Earth only by the slowest possible thread of communication. The psychological term for this kind of rupture, this severance from one's cultural and temporal context, is something researchers are only beginning to have the vocabulary to describe. Some have borrowed the term solastalgia, originally coined to describe the grief people feel when their home environment is irrevocably changed around them. But what an interstellar crew would experience goes beyond that. It is more like a kind of existential displacement, the knowledge that the world you belong to is moving on without you, and that when and if you return, you will be a stranger in it. Let me tell you about a study that has never left my mind since I first read it. In 2019, psychologist Lawrence Palinkas, one of the world's leading experts on the psychology of isolated and confined environments, and a researcher who has spent considerable time studying Antarctic winter-over crews, published an analysis of what he calls the behavioral health risks of long-duration spaceflight. In it, he identified several distinct psychological challenges that he considers essentially inevitable in any crew undertaking a mission of significant duration and distance. The first is interpersonal conflict. In any small group of people confined together for long periods, friction is not a possibility, it is a certainty. The research from Antarctic stations, from submarines, from space station missions consistently shows that interpersonal tensions escalate over time, even among highly selected, highly trained, deeply professional individuals. The things that become sources of conflict are often not dramatic, they are mundane. The way someone chews their food, the way someone else always takes slightly too long in the shared bathroom, the sound of a particular laugh heard 1,000 times in a confined space. These micro-irritations accumulate, they compound, and in an environment where there is nowhere to go, no third party to consult, no change of scenery to reset your nervous system, they can metastasize into something far more serious. The second is what Palinkas calls autonomy and control, or more precisely, the progressive erosion of it. On a long mission, crew members are following protocols developed by people on Earth who have never experienced what the crew is experiencing, responding to directives that arrive with a 4-year time delay, making decisions about their own lives and bodies based on information that is already years out of date by the time it reaches them. The psychological need for agency, for the feeling that you have meaningful control over your own circumstances, is one of the most fundamental human needs we know of. Persistent deprivation of it is associated with depression, learned helplessness, and a collapse of motivation. The third risk, and this one is perhaps the most philosophically challenging, is something Palinkas describes as a loss of meaning. In our ordinary lives, meaning is constructed from a web of relationships, responsibilities, and contexts. Your work matters because it affects people you know. Your choices carry weight because they ripple out into a world you are embedded in. Your identity is shaped and reflected back to you constantly by the social environment you inhabit. Strip all of that away, reduce the social world to 5 or 11 other people. Sever the connection to the civilization that gave your life its context, and ask yourself, what does it mean to do anything? What does it mean to be anyone? When the crew of a ship bound for Proxima Centauri looks out their viewport at the absolute darkness between the stars, no planets, no nebulae, just the thin, cold scatter of distant suns, what story do they tell themselves about why they are there, and whether it is worth it? This is not an abstract philosophical question. It is a mission-critical one, because meaning is not a luxury. It is, as the psychiatrist and Holocaust survivor Viktor Frankl argued in perhaps the most important psychological text of the 20th century, the central organizing principle of human resilience. People endure almost anything, pain, loss, deprivation, fear, when they have a sufficiently powerful reason to endure it, and they collapse under far lesser burdens when they do not. The psychological architecture of an interstellar mission, the rituals, the structures, the shared narratives, the sources of purpose, would need to be as carefully engineered as the life support system, maybe more carefully, because a life support system failure kills the body. A meaning failure kills the will to live. And on a 20-year journey with no rescue possible, a crew that loses its collective will is a crew that has lost everything. Some researchers have turned to history for models. The long sea voyages of the Age of Exploration, Magellan's circumnavigation, Cook's Pacific's expeditions, involved crews isolated for years from their home societies. What kept those crews coherent? Partly discipline, partly fear, partly the clear hierarchical structures of naval command, which reduced decision-making ambiguity and gave individuals defined roles. Some historians argue that ritual played a crucial role. The daily rhythms of a ship at sea, the ceremonies of navigation, the marking of time through shared practices, all created a kind of cultural membrane that held the social group together. On an interstellar mission, researchers have proposed something similar, the deliberate engineering of what they call psychosocial countermeasures. Scheduled social rituals, structured periods of collective activity, carefully designed interior environments that simulate the passage of seasons or the rhythm of day and night, virtual reality environments so immersive and varied that they provide genuine psychological respite from the monotony of the ship. Even the possibility of Earth-like gardens inside the ship, living plants, soil, the smell of something growing, as a way of maintaining a biological and emotional connection to the world left behind. These are not frivolous ideas. They are being taken seriously in the literature on long-duration spaceflight psychology, because the researchers working on this problem understand something profound. You cannot send biological, psychological human beings on a 20-year journey and treat their inner lives as an afterthought. The mission's success depends as much on the health of the mind as on the integrity of the hull. And this brings me to a question that I find one of the most genuinely fascinating in all of this. Not a question about technology or biology or psychology in isolation, but a question that cuts across all of them. Is the human being, as we currently exist, shaped by millions of years of evolution on the surface of a warm, blue, crowded, noisy, beautiful planet, actually the right kind of entity to make this journey? Or would an interstellar mission require something that is, in some meaningful sense, no longer quite human? Not a robot, not an artificial intelligence, though those will certainly play a role, but a human being who has been sufficiently modified biologically, neurologically, psychologically, that the creature arriving at Proxima Centauri is genuinely different from the one that left Earth. This is the question that keeps philosophers, bioethicists, and scientists up at night, and it is the question we are going to sit with now, because here is what I want you to carry with you into that next section. Everything we have talked about so far, the radiation tearing at neurons, the circadian disruption, the slow erosion of meaning and identity, all of it is a message from the universe, a very clear, very specific message. It says, you are not built for this, not yet. And the question of what it would take to become built for it, that is not just a scientific question, it is a deeply human one. Because it asks us to decide what we are willing to change about ourselves and what we are not willing to lose. It asks us where the boundary is between enhancement and transformation, between becoming better and becoming something else entirely. That conversation is one of the most important our species will ever have, and it is already beginning. If you are enjoying this journey, make sure to give this video a thumbs up. Takes 1 second but makes all the difference. Your support really means a lot to me. Let me ask you something that I genuinely want you to sit with for a moment before we move forward. If you could modify your own biology, not to cure a disease, not to fix something broken, but to make yourself capable of something your body was never designed to do, would you? And if the alternative was never reaching the stars, never crossing that 4.24 light-year gulf, never knowing what waits on the other side, would that change your answer? Because that is the conversation happening right now in research labs, in bioethics departments, in the pages of peer-reviewed journals, and in the quiet, careful deliberations of space agencies that are starting to reckon with a fundamental truth. The human body, in its current form, may simply be the wrong tool for the job. Not because we are fragile, we are remarkably resilient, actually. 3.8 billion years of evolution have produced an organism of extraordinary adaptability. But that adaptability was shaped by one very specific environment. Gravity, atmosphere, sunlight, seasons, a planet teeming with other life, a social world of hundreds or thousands of individuals. Remove all of that, and the same evolutionary pressures that made us so magnificently suited to Earth become liabilities in the void between stars. So what do we do about it? Let's start with what is already happening, not speculation, not science fiction, but active, funded, peer-reviewed science that is pushing the boundaries of what human biology can be. In 2012, a team of researchers at Harvard Medical School led by geneticist George Church began working on what he called the Human Genome Project Right. The ambition not just to read the human genome, as the original Human Genome Project did, but to synthesize it from scratch and rewrite it with deliberate improvements. Church has been remarkably public about the kinds of modifications he believes could be relevant to long-duration spaceflight. He has spoken openly about the possibility of engineering human cells with enhanced DNA repair mechanisms, borrowing genetic sequences from organisms like Deinococcus radiodurans, a bacterium so extraordinarily resistant to radiation that it can survive doses thousands of times higher than what would kill a human being. Scientists sometimes call it Conan the bacterium. It can reconstruct its own shattered genome from hundreds of fragments. It thrives in environments that are essentially lethal to every other known organism. The question Church and others are asking, and it is a serious scientific question, not a rhetorical one, is whether the genetic architecture underlying that kind of radiation resistance could be partially incorporated into human cells. Not to turn people into bacteria, but to give our cells a dramatically enhanced capacity to detect, respond to, and repair the DNA damage caused by galactic cosmic rays. Is this possible? The honest answer is, we do not know yet. The biology is staggeringly complex. Dinococcus radiodurans achieves its radiation resistance through a combination of mechanisms, extraordinarily efficient DNA repair enzymes, high concentrations of certain antioxidant compounds, a unique cellular structure that keeps its genome densely packed and therefore more resistant to fragmentation. Transplanting even pieces of that system into human cells would be a monumental engineering challenge, but the conceptual direction is legitimate, and the early molecular biology is being actively explored. Now let's go a level deeper. Because genetic modification of somatic cells, the ordinary cells of the body, as opposed to reproductive cells, is already happening in medicine. CRISPR-based therapies are being used right now to treat sickle cell disease, certain cancers, and a handful of other genetic conditions. The technology is real, it is advancing rapidly, and its potential scope is expanding every year. But what researchers working on the interstellar biology problem are beginning to discuss goes beyond therapeutic modification. They are talking about what some call directed evolution, the deliberate, engineered acceleration of biological change that would normally take tens of thousands of years of natural selection, compressed into a generation or two of intentional design. In 2019, a paper published in the journal Futures by a team including space bioethicist James Schwartz outlined a framework for what they called enhancement for space, a taxonomy of biological modifications that could, in principle, make human beings more suitable for long-duration spaceflight. The list included enhanced radiation resistance, as we discussed, but it also included modifications to bone density maintenance, because the progressive loss of bone mass in microgravity is one of the most persistent and serious physiological challenges of spaceflight, and current countermeasures like exercise regimens are only partially effective over very long periods. It included modifications to the vestibular system, the inner ear structures responsible for balance and spatial orientation, which become chronically confused in microgravity and contribute significantly to space sickness and long-term neurological disorientation. And it included, most provocatively, modifications to the psychological and neurological systems governing mood, stress response, and social behavior. That last category is where the bioethical conversation gets genuinely intense. Think about what it would actually mean to engineer a human being for psychological compatibility with 20 years of extreme isolation. We know from the neuroscience that a significant component of our emotional responses, our capacity for loneliness, our need for novel stimulation, our sensitivity to social rejection, our tendency toward depression under conditions of helplessness, is rooted in specific neurochemical systems. Serotonin, dopamine, norepinephrine, oxytocin, these are not just the poetry of neuroscience. They are molecular systems shaped by millions of years of selection pressure toward behaviors that maximized survival and reproduction in social groups on the African savanna. An interstellar crew does not need the neurochemistry of the African savanna. They need something different, something calmer, something more internally self-sufficient, something less dependent on the constant social stimulation and environmental novelty that our brains have evolved to crave. Could we engineer that? Could we, through some combination of genetic modification and targeted neurological intervention, reduce the biological drive for novelty without eliminating creativity? Could we dampen the neurochemical machinery of loneliness without eliminating the capacity for connection? Could we recalibrate the stress response system so that it remains functional and protective without tipping into the chronic anxiety that isolation tends to produce? Theoretically, some neuroscientists say Yes, in principle, these are not impossible targets. The neurochemical systems involved are known. The genetic variants that influence them are being mapped with increasing precision by large-scale studies like the UK Biobank, which has linked thousands of genetic markers to measurable differences in psychological traits across hundreds of thousands of participants. But here is the bioethical wall you run straight into. If you modify a human being's neurochemistry to make them more psychologically suited to isolation, to make them need other people less, to dampen the ache of loneliness, to reduce the hunger for novelty and stimulation, have you made them better? Or have you taken something away from them that was essential to who they were? Because those drives, the need for connection, the hunger for experience, the ache of absence, are not bugs in the human system. They are features. They are what motivates art and music and love and every act of extraordinary courage and tenderness our species has ever produced. They are, in a very real sense, what makes us us. So the question becomes, at what point does a human being optimized for interstellar travel stop being human in any meaningful sense? And who has the right to make that decision, for themselves, and especially for the children who might be born aboard that ship, who never had a choice about the world they were brought into? That last point, children born in space, is one that the scientific and ethical literature is only beginning to grapple with seriously, and it deserves more than a passing mention. Some proposals for interstellar travel, particularly those involving generation ships, where the journey is too long for any individual to complete in a single lifetime, explicitly involve the birth and raising of children aboard the vessel. These children would never know Earth. They would grow up in an artificial environment, under artificial gravity, if the ship can provide it, breathing recycled air, eating food grown in hydroponic bays, with the stars visible only through viewports or cameras. Their entire experiential world, every sight, sound, smell, texture, social interaction would be bounded by the interior of a spacecraft. What kind of human being does that produce? We genuinely do not know. We have never done it. The developmental psychology of spaceborne humans is at this point almost entirely theoretical. What we do know from developmental psychology on Earth is that the environments children grow up in shape their brains profoundly and permanently. The range of sensory experience available in early childhood, the diversity and quality of social interactions, the presence or absence of nature, of physical space to explore, of unpredictability and novelty, all of these factors influence the development of neural architecture in ways that persist throughout life. A child who grows up in a rich, varied, stimulating environment develops a brain that is measurably different from one raised in deprivation. What would a ship-raised child's brain look like? Would it be adapted in the way that humans have always adapted to their environments, to the specific demands of the ship? Would it be, in some ways, more suited to the voyage than its earthborn parents? Or would the narrowness of that world impose costs, cognitive, emotional, developmental, that we cannot yet predict? And then there is the ethical dimension that sits above all of this like a storm cloud. Those children did not consent to be born into a spacecraft. They did not choose the mission. They did not choose their world. They cannot opt out. Is it ethical to bring a human being into existence in circumstances so fundamentally constrained, so utterly removed from the full range of human experience, for the sake of a mission their ancestors decided was worth undertaking? These are not comfortable questions. They are not meant to be. They are the questions that serious bioethicists, people like Charles Cockle at the University of Edinburgh, who has written extensively on the ethics of space exploration, and Konrad Socik, whose work on the human factors of interstellar travel I find consistently rigorous and unsettling, are beginning to put at the center of the conversation about humanity's long-term future in space. Now, I want to bring in a perspective that I think is crucial and often missing from these discussions, because everything I have described so far, the genetic modification, the neurological engineering, the generation ship dilemmas, tends to be framed as a problem to be solved, a series of obstacles between us and the stars that sufficiently clever science and sufficiently brave ethics can eventually overcome. But there is another way to look at it. What if the journey to Proxima Centauri, with all of its biological and psychological demands, is not a problem to be solved but an invitation to evolve, not in the passive, generational sense of natural selection, but in the active, intentional sense of a species choosing, with open eyes, to become something more than it currently is. The cosmologist and author Carl Sagan wrote something in his book Pale Blue Dot that has stayed with me ever since I first read it. He said, "Exploration is in our nature. We began as wanderers, and we are wanderers still." And I think about that in the context of what we are discussing today, and I wonder whether the willingness to face what an interstellar journey demands, the willingness to look at all of those biological and psychological challenges and say, we will figure this out, is itself a form of the same impulse that drove the first humans across land bridges into unknown continents. The same impulse that drove Polynesian navigators across thousands of kilometers of open Pacific in outrigger canoes, navigating by stars and swells and the behavior of birds. The same impulse that drove every explorer who has ever stood at the edge of the known world and chosen to take one more step. We have always transformed ourselves in the act of exploring, not genetically, not yet, but culturally, technologically, psychologically. Every frontier we have crossed has required us to develop new tools, new skills, new ways of thinking about who we are and what we are capable of. The frontier of interstellar space is simply the most extreme version of that process our species has ever contemplated. And perhaps this is the thought I want to leave you with as we move toward the next section. Perhaps the most human thing about us is not any particular biological configuration or psychological trait. Perhaps the most human thing about us is the refusal to accept that we are finished, the insistence that whatever we are today is not the final answer, the conviction written into our history and our science and our art that the story is still going, that the next chapter has not yet been written, because here is what we have not talked about yet. Here is the part of this story that might be the most extraordinary of all. We have been assuming throughout this video that the crew traveling to Proxima Centauri would be doing so in order to arrive, look around, and perhaps return. But what if the destination itself changes everything? What if the system around Proxima Centauri, which we already know with a reasonable degree of scientific confidence, contains at least one planet, offers something that reframes every sacrifice the journey demands? Proxima Centauri b, a world orbiting our nearest stellar neighbor. And what we know about it, and what we do not yet know, and perhaps most importantly what we might find, is where we are going next. Because the story of Proxima Centauri b is one of the most tantalizing and unresolved in all of contemporary astronomy. And it turns out that the destination might be just as terrifying as the journey. In ways nobody is talking about, let me paint you a picture. Imagine standing on a world that is not Earth. The sky above you is not blue. It is a deep, bruised reddish-orange, lit by a sun that hangs permanently fixed on the horizon, never rising, never setting, locked in place like a nail driven into the sky. One half of the world behind you is frozen in eternal darkness, temperatures plunging to hundreds of degrees below zero. One half in front of you bakes in perpetual, unblinking daylight, and every few days, sometimes every few hours, that dim red sun above the horizon erupts. Not gently, not distantly, it detonates, hurling a wall of radiation and charged particles across the surface with an intensity that would strip an unprotected human being to nothing in minutes. This is not a world from a nightmare. This is Proxima Centauri b, as best as current science can reconstruct it, and it is, at least by one measure, the most important piece of real estate in the known universe. Because it is the closest thing to another world our species has ever had genuine reason to contemplate visiting. So let's talk about what we actually know, and equally importantly, what we do not. Proxima Centauri b was first confirmed in 2016 in a landmark paper published in the journal Nature by a team led by Guillaume Anglada Escudé of Queen Mary University of London. The discovery was made using the radial velocity method, detecting the tiny, periodic wobble that a planet's gravitational pull induces in its host star as it orbits. The wobble is minuscule. We are talking about measuring a star moving back and forth at speeds of roughly 1.5 meters per second, roughly the pace of a slow walk, across a distance of 4.24 light-years. The precision required to detect that signal is, when you truly appreciate it, one of the most remarkable achievements in the history of observational astronomy. What the data told us was this: Proxima Centauri b has a minimum mass of approximately 1.17 times the mass of Earth, making it what astronomers call a super-Earth, or potentially an Earth-mass planet. It orbits its star at a distance of roughly 0.048 astronomical units. For reference, 1 astronomical unit is the average distance between Earth and the Sun, approximately 149.6 million kilometers. Proxima Centauri b sits about 7.3 million kilometers from its star. That sounds extraordinarily close, and it is, by the standards of our solar system. Mercury, our innermost planet, orbits at roughly 57.9 million kilometers from the Sun. Proxima b is nearly 8 times closer to its star than Mercury is to ours. And yet, and this is the crucial detail, Proxima Centauri is not our Sun, not even close. Proxima Centauri is a red dwarf star, spectral class M5.5. It is approximately 100 times less luminous than the Sun, meaning it radiates far less energy across all wavelengths. It has a surface temperature of around 3040 degrees Celsius, compared to the Sun's approximately 5500 degrees Celsius. It is so dim that despite being our nearest stellar neighbor, it is completely invisible to the naked eye from Earth. You cannot see it without a telescope because it radiates so much less energy. A planet needs to orbit much closer to a red dwarf to receive enough warmth to potentially maintain liquid water on its surface, the standard benchmark for what astronomers call the habitable zone. And Proxima b, orbiting at that tight 7.3 million kilometer distance, sits right in the middle of Proxima Centauri's habitable zone. On paper, the energy budget works out. The amount of stellar radiation Proxima b receives is broadly comparable to what Earth receives from the Sun. That single fact, that Proxima b sits in the habitable zone of its star, is what turned this discovery into one of the most electrifying moments in modern astronomy. Here was a potentially Earth-mass planet in the habitable zone, around our nearest stellar neighbor. The proximity alone, 4.24 light-years, essentially next door by cosmic standards, made it immediately the most discussed exoplanet in the world. But proximity to a habitable zone does not a habitable world make. And the more deeply scientists have examined the specific nature of Proxima Centauri and its relationship with Proxima b, the more complicated, and in some ways darker, the picture has become. The first major complication is tidal locking. When a planet orbits very close to its star, the star's gravitational field exerts a differential pull across the near and far sides of the planet. Over geological timescales, this differential, called tidal force, gradually slows the planet's rotation until one side permanently faces the star and the other permanently faces away. The planet stops rotating relative to its star. This is called tidal locking, and it is essentially certain to have occurred on Proxima b. given the tightness of its orbit and the age of the system. Proxima Centauri is estimated to be approximately 4.85 billion years old, somewhat older than our own Sun. What does a tidally locked world look like? The day side, the hemisphere permanently facing the star, receives constant stellar radiation. Temperatures there could potentially be quite warm, though the exact values depend heavily on factors like atmospheric composition and circulation patterns that we cannot yet measure. The night side, permanently turned away from the star, receives no direct stellar radiation whatsoever and would be extraordinarily cold, potentially cold enough for gases like carbon dioxide and nitrogen to freeze out of any atmosphere and precipitate onto the surface as frost. Now, a planet does not have to be uniformly habitable to be habitable at all. Some researchers have proposed that a tidally locked planet with a sufficiently thick atmosphere could redistribute heat from the day side to the night side through atmospheric circulation, essentially a permanent planet-encircling wind system driven by the temperature differential. Under the right conditions, a band of relatively temperate, potentially habitable environment might exist along the terminator, the boundary between the eternal day and eternal night hemispheres. Some have poetically called this the Ring of Life scenario. It is a genuinely exciting idea, but it rests on a stack of assumptions about atmospheric composition, pressure and stability that we currently cannot verify. And it runs directly into the second major complication, the one that, the more I learn about it, I find the most viscerally alarming of all the challenges Proxima b presents. Proxima Centauri is a flare star. This needs to sit with you for a moment, because I think the casual use of the word flare undersells what we are actually talking about. Our Sun produces solar flares, eruptions of energy and charged particles from its surface. Large solar flares directed toward Earth can disrupt satellite communications, damage power grids, and pose radiation risks to astronauts outside the protective envelope of Earth's magnetic field and atmosphere. The most powerful solar flare ever recorded in the instrumental era, the X-28 event of November 2003, released an extraordinary amount of energy. Space weather forecasters take large solar flares seriously because even at a distance of 149 million kilometers, their effects can be significant. Proxima Centauri produces flares that are, in some cases, orders of magnitude more powerful relative to its size, and it produces them constantly. In March 2016, the same year Proxima b was confirmed, astronomers using the Evolutionary telescope array detected what has since been called the Proxima Centauri superflare. In a matter of minutes, the star brightened by a factor of approximately 68 in the near ultraviolet band, 68 times its normal output. In 2 minutes, this superflare would have bathed Proxima b in a ferocious flood of ultraviolet radiation, the kind that destroys organic molecules, breaks down atmospheric ozone, and renders surface environments inhospitable to life as we know it. And this was not a rare event. Analysis of Proxima Centauri's behavior over extended observation periods has shown that it produces large flares, events comparable in energy to significant solar flares from our Sun, at a rate of roughly 1 per day. Smaller flares occur even more frequently. The star is not occasionally volatile. It is persistently, relentlessly, almost habitually explosive. Now consider what this means for an atmosphere. One of the most important functions of a planetary atmosphere, from a habitability perspective, is as a shield. Earth's atmosphere, combined with our planet's magnetic field, absorbs and deflects the vast majority of the harmful radiation and energetic particles that the Sun throws at us. Without it, Earth's surface would be sterilized. Proxima b's atmospheric situation is deeply uncertain, and the flare environment is a central reason why. Every major flare event strips away the upper layers of a planetary atmosphere, through a process called atmospheric sputtering. High-energy particles physically knock atmospheric molecules off into space. Over billions of years of constant flare bombardment, it is entirely possible, some researchers say likely, that Proxima b has lost a significant fraction of any atmosphere it once possessed. A 2017 study published in the Astrophysical Journal Letters modeled the atmospheric erosion of Proxima b under realistic flare conditions and concluded that an Earth-like atmosphere could be substantially depleted over geological timescales, particularly in the absence of a strong planetary magnetic field. Does Proxima b have a magnetic field? We do not know. We currently have no way to measure it directly at this distance. A magnetic field requires a planet to have a partially molten, electrically conducting interior in active motion, a planetary dynamo. Whether Proxima b has such an interior depends on its composition, its thermal history, and factors we cannot yet constrain with the data available. It is an open question, a vitally important one, so here is the honest scientific picture as of right now. Proxima b is a real planet. It is approximately Earth mass. It orbits in its star's habitable zone. It is the closest known exoplanet to Earth. These facts are solid. Everything else, whether it has an atmosphere, what that atmosphere consists of, whether it has liquid water, whether it has a magnetic field, whether any part of its surface could support life, is currently unknown. Not uncertain in a minor, fill-in-the-deals kind of way. Unknown in a fundamental, we have almost no data kind of way. The James Webb Space Telescope, the most powerful space observatory ever built, has the theoretical capability to study the atmospheres of nearby exoplanets through a technique called transmission spectroscopy, analyzing starlight that passes through a planet's atmosphere as it transits in front of its star. However, Proxima b's orbital inclination, as far as we can tell, means it likely does not transit across the face of Proxima Centauri from our viewing angle. That makes atmospheric characterization through this method essentially impossible with current technology. Future planned observatories, including the extremely large telescope currently under construction in Chile's Atacama Desert, with its 39-meter primary mirror, may be able to directly image Proxima b and analyze reflected starlight from its surface, potentially revealing signatures of atmospheric gases. This is one of the most eagerly anticipated capabilities of the next generation of ground-based astronomy. But we are talking about instruments that will not reach full operational capacity until the late 2020s at the earliest, and the science of atmospheric characterization at these distances is extraordinarily difficult. The point is this: if a crew were to make the journey to Proxima Centauri, enduring everything we have discussed in the previous sections, the radiation, the psychological isolation, the biological transformation, they would be arriving at a destination they know almost nothing about in advance. They would be stepping off their ship after 20 years in the void into a system that might be everything they hoped for, or might be utterly, lethally hostile to unprotected human life, and they would have no way of knowing which until they got there. Now, some researchers have proposed that robotic precursor missions following the breakthrough Starshot concept of laser-propelled miniature probes could be sent ahead of any crewed mission to characterize the Proxima Centauri system in detail. A probe traveling at 20% of the speed of light would reach the system in roughly 20 to 25 years, spend time gathering data, and then, and this is where it gets complicated, transmit that data back to Earth at the speed of light, taking another 4.24 years to arrive. So humanity's first detailed close-up data from Proxima Centauri would arrive roughly 25 to 30 years after such a probe was launched. That is within the span of a human lifetime. Someone alive today could conceivably receive news from Proxima Centauri before they die. but transmitting useful data from a gram-scale probe, one small enough to be accelerated by a laser array to those extraordinary speeds, is itself a formidable engineering challenge. The antenna systems required, the power generation, the data compression, the pointing precision needed to direct a signal across 4 light years, these are not trivial problems. Breakthrough Starshot's own documentation acknowledges them as among the most significant technical hurdles of the concept. It is being worked on, but it is not solved. And so we arrive at a place that I think is one of the most profound in this entire conversation. A place where the science, the engineering, the biology, the psychology and the philosophy all converge. We are talking about sending human beings, or whatever human beings might need to become, to a destination we know almost nothing about, across a distance that no living thing has ever crossed, in vessels we have not yet built, powered by technologies we have not yet mastered, to a world orbiting a star that seems almost designed to make surface life difficult, and yet the conversation is happening, the papers are being written, the simulations are being run, the telescopes are being built, the laser arrays are being designed. The bioethicists and the neuroscientists and the geneticists are gathering around the same table and asking the same question: how do we make this possible? There is something about that, something about the sheer, unrelenting human audacity of it that I find genuinely moving, because it tells us something about what we are, not just as scientists or engineers or dreamers, as a species. We look at the impossible and we do not look away. We lean in, but leaning in does not mean pretending the challenges are smaller than they are. It means understanding them in their full depth and complexity. And there is one more dimension of this journey, one more layer of strangeness and difficulty and wonder that we have not yet touched. What happens to time itself on this journey? Not philosophically, physically, because at the velocities we are discussing, even a fraction of the speed of light, the universe stops behaving the way your intuition tells you it should. Einstein's special relativity kicks in, and it does so in ways that are simultaneously beautiful and deeply, deeply disorienting. At 20% of the speed of light, the breakthrough Starshot target velocity for unmanned probes, time dilation effects are relatively modest but measurable. A clock aboard the ship would run slightly slower than a clock on Earth. But for crewed missions under more ambitious propulsion scenarios, missions traveling at 50 or 60 or even 90% of the speed of light, the effects become dramatic. A crew traveling at 90% of the speed of light would experience time passing at roughly 44% the rate of an observer on Earth. A journey that takes 10 years from Earth's perspective would feel like 4.4 years to the crew. They would arrive at Proxima Centauri biologically younger than the people who watched them leave, and they would return, if they returned, to a world that had aged far more than they had. This is not theoretical, this is measured physics. Atomic clocks aboard fast-moving aircraft and satellites show exactly this effect, precisely as Einstein predicted. At the velocities of interstellar travel, it becomes not a curiosity but a defining feature of the mission, one with profound implications for the crew's psychological relationship to time, to Earth, and to their own sense of self. Because what does it mean to leave Earth as a 30-year-old, travel to Proxima Centauri, and back in what feels to you like 8 years, and return to find that your children are now middle-aged, that your friends have grown old or died, that the world has moved on by decades while you experienced only years? What does that do to a person, to their sense of belonging, to their identity? That is the question that closes this part of our journey, and it opens directly into something even more fundamental. The question of what this mission would mean, not just technically, not just biologically, but cosmically. In the context of the 4 billion-year story of life on this planet, and the 13.8 billion year story of the universe itself, that is where we go next. If you are still watching, then you already know this channel speaks your language. Don't forget to subscribe and hit the like button. Every video we take a real question about the cosmos and follow it all the way down. Be part of this community. There is a thought experiment I want you to try. Not a complicated one, no mathematics required, no physics degree necessary. Just your imagination and a willingness to sit with something genuinely uncomfortable. Picture someone you love, a parent, a sibling, a best friend, a partner, someone whose face you know so well you could draw it from memory, someone whose laugh you could pick out of a crowded room. Now imagine saying goodbye to them on a launch pad, hugging them, looking at their face one last time, and then stepping aboard a ship that will carry you away at a significant fraction of the speed of light. You are gone for what feels to you like 8 years. 8 years of the void, of recycled air, of the same faces in the same corridors, of a red dwarf growing slowly brighter in the forward viewport. 8 years of your own biological time, your own heartbeats, your own aging cells, and then you come home, and the person you hugged on that launch pad is now 20 years older than when you left, or 30, or they are gone entirely, buried in ground you were not there to stand beside, at a funeral you could not attend, at a moment when they needed someone, and you were 4 light years away moving through the dark. You have not failed them, you have not abandoned them, you simply obeyed the laws of physics, and the laws of physics do not care about love. This is time dilation. And at the velocities required for interstellar travel within anything resembling a human lifespan, it stops being an abstract concept and becomes one of the most intimate and devastating features of the journey. Let me walk you through the actual numbers, because I think precision matters here. I want you to feel the reality of this, not just understand it conceptually. Einstein's special theory of relativity, published in 1905, contains within it a relationship between velocity and time. As an object moves faster relative to a stationary observer, time for the moving object passes more slowly relative to the stationary observer. This is not an illusion, it is not a perceptual trick, it is a fundamental feature of how space-time works, confirmed experimentally to extraordinary precision across more than a century of measurement. The mathematical relationship is described by something called the Lorentz factor, represented by the Greek letter gamma. At everyday speeds, running, driving, even flying in a jet aircraft, the Lorentz factor is so close to 1 that the time dilation effect is completely negligible. Your watch does not meaningfully slow down on a transatlantic flight. The effect is real but measured in nanoseconds, but as you approach the speed of light, the Lorentz factor grows dramatically, and the effects become anything but negligible. At 10% of the speed of light, approximately 29,900 kilometers per second, the Lorentz factor is approximately 1.005. Time aboard the ship passes at about 99.5% the rate of time on Earth. The difference over a 20-year journey would be modest, roughly a few weeks. Not yet dramatic, not yet life-altering. At 50% of the speed of light, the Lorentz factor rises to approximately 1.15. Time aboard the ship passes at about 87% the rate of Earth time. On a journey of 20 years from Earth's perspective, the crew would experience roughly 17.5 years, still close, still within the same order of magnitude. At 90% of the speed of light, the Lorentz factor reaches approximately 2.3. Time aboard the ship passes at roughly 44% the rate of Earth time. A journey that takes 22 years from Earth's perspective would feel like about 9.6 years to the crew. Now the gap is becoming significant. While the crew ages by less than a decade, Earth ages by more than 2 decades. At 99% of the speed of light, the Lorentz factor climbs to approximately 7.1. A 20-year Earth-time journey would be experienced by the crew in less than 3 years. Earth would be aging 7 times faster than the people on the ship. And at 99.9% of the speed of light, the Lorentz factor reaches approximately 22. Now a crew could theoretically travel to Proxima Centauri and back, 4.24 light-years each way, roughly 8.5 light-years round trip, and experience only a matter of months aboard the ship, while nearly 9 years passed on Earth. These are real numbers. They come directly from the mathematics of special relativity, mathematics that have been tested and confirmed to extraordinary precision in particle accelerators, in atomic clocks, in the GPS satellite network that you use every time you ask your phone for directions. The satellites of the GPS system have to account for relativistic time dilation in their clocks in order to maintain the accuracy required for navigation. If the engineers who designed GPS had ignored relativity, the system would drift by kilometers per day. They did not ignore it, and it works. Now, here is the practical catch that immediately deflates some of the excitement those numbers might generate. Reaching 90% of the speed of light is not simply a matter of going faster. It requires energy, staggering civilization-scale amounts of energy. The relationship between kinetic energy and velocity is not linear. It becomes increasingly steep as you approach the speed of light, because of the very same relativistic physics that creates time dilation. The closer you get to the speed of light, the more energy each additional increment of speed requires, approaching infinity as you approach the ultimate speed limit. To accelerate a crewed spacecraft, let's say a vessel of 1,000 metric tons, which is actually quite modest for a ship capable of supporting humans for years, to 50% of the speed of light and then decelerate it again at the destination, would require an amount of energy roughly equivalent to the entire global energy consumption of Earth for several decades, depending on the efficiency of the propulsion system. To reach 90% of the speed of light would require orders of magnitude more. Where does that energy come from? No existing or near-future technology can provide it. The most energetically dense fuel known to physics is matter-antimatter annihilation, which converts 100% of mass into energy, as described by Einstein's most famous equation. A matter-antimatter drive, if it could be built, would be by far the most efficient rocket propulsion system physically possible. But producing antimatter is itself extraordinarily energy-intensive. Current particle accelerator methods produce antimatter at efficiencies so low that generating a single gram would require more energy than currently produced by all of human civilization combined, and would take millions of years at current production rates. Other concepts on the table include nuclear pulse propulsion, the Orion concept, in which a spacecraft is propelled by a series of nuclear explosions detonated behind it. This is perhaps the most technologically near-term option for achieving significant fractions of the speed of light with a large payload, but it comes with obvious political and practical complications, and even optimistic estimates put achievable velocities at a few % of the speed of light. Useful, but far from the relativistic regime where time dilation becomes dramatically significant. Then there is the concept of a Bussard ramjet, a theoretical spacecraft that would scoop interstellar hydrogen with an enormous electromagnetic funnel and use it as fuel for a fusion reactor. The appeal is obvious. No need to carry fuel, because the fuel is everywhere in space. The reality is considerably more complicated. Interstellar space contains about 1 hydrogen atom per cubic centimeter on average, far too sparse to sustain meaningful fusion at any velocity we could achieve, and the drag created by scooping that sparse medium might actually slow the ship more than the fusion would accelerate it. Most physicists consider the Bussard ramjet, in its original conception, non-viable. Modified versions are still discussed but remain highly speculative. What all of this means is that the time-dilating, relativistic interstellar journey, the kind where a crew returns home to find decades have passed while they experienced only years, is not simply an engineering challenge waiting for a clever solution. It is a challenge that sits at the intersection of fundamental physics, energy economics, and material science in ways that do not yield to any obvious near-term path. And yet it is precisely the kind of challenge that our species has historically been worst at predicting correctly. The history of technology is littered with problems that seemed intractable until they suddenly were not. Nuclear fission was considered by some eminent physicists to be practically unachievable mere years before the first reactor went critical. The idea of a global computer network connecting billions of people in real time would have seemed like pure fantasy to the brightest minds of 1950. Heavier than air flight was dismissed as impossible by serious scientists just years before the Wright brothers proved otherwise. So I hold the propulsion problem with a kind of respectful uncertainty. It is real, it is enormous, it may take centuries to solve, but I am not willing to declare it permanently impossible, because the history of science suggests that permanently impossible is a phrase we should deploy with great caution. Now I want to shift perspective again, because we have been talking about time dilation primarily as a challenge, as something that happens to the crew and separates them from the world they left. But there is another way to look at it that I find almost overwhelmingly beautiful. Time dilation means that a sufficiently fast ship is, in a sense, a time machine. Not backward, the physics do not allow that, but forward. A crew traveling at a high fraction of the speed of light could, in principle, traverse not just 4 light-years but hundreds, thousands. They could, within their own biological lifetimes, reach star systems that are tens or even hundreds of light-years away, while thousands of years passed on Earth. This means that the stars are not necessarily out of reach for individual human beings. They are out of reach at our current velocities, but the universe does not forbid a human being from traveling to distant stars within a single lifetime. The physics allow it. The energy and engineering do not yet. But the universe has left a door open, written into the very mathematics of space-time. Some physicists find this deeply suggestive. Frank Tipler, Michio Kaku, and others have written about what they call the ultimate potential of relativistic travel, the possibility that a sufficiently advanced civilization could effectively explore the entire observable galaxy within a single human lifetime of shipboard time simply by traveling fast enough. The galaxy is roughly 100,000 light-years in diameter. At velocities close enough to the speed of light, a crew could cross it in decades of their own experienced time. The universe, in other words, is not as large as it appears to a stationary observer. To someone moving fast enough, it shrinks. Time compresses. The cosmos becomes, in some wild and wonderful sense, traversable. That idea does something to me every time I sit with it. It feels like the universe is saying something, like there is a message encoded in the physics, a door that can only be opened by those willing to pay the extraordinary price of admission. But here is where I need to bring in a perspective that I think is absolutely essential, and that does not get nearly enough attention in popular discussions of interstellar travel. A perspective that comes not from engineering or biology or psychology, but from cosmology, from the largest possible view of what the universe is doing and where it is going. We live in an expanding universe. You probably know this. Edwin Hubble confirmed it observationally in 1929, and it has been one of the foundational facts of cosmology ever since. The universe began in an extraordinarily hot, dense state approximately 13.8 billion years ago, the event we call the Big Bang, and has been expanding ever since, carrying galaxies away from each other on the fabric of space-time itself. What is less commonly discussed and what has profound implications for the long-term future of interstellar and intergalactic exploration is that this expansion is accelerating. In 1998, two independent research teams, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Reis, made a discovery so surprising that it earned them the Nobel Prize in Physics in 2011. Studying distant Type Ia supernovae as standard candles for measuring cosmic distances, they found that the universe was not simply expanding, it was expanding faster and faster over time. Something was pushing the universe apart with increasing urgency. We call this something dark energy. We do not know what it is. It constitutes approximately 68% of the total energy content of the universe, making it by far the dominant component of the cosmos, and we have essentially no idea what it fundamentally is. What this accelerating expansion means for the very long-term future of exploration is staggering. As the universe expands faster and faster, distant galaxies recede from us at increasing speeds. Beyond a certain distance, the cosmic event horizon, galaxies are already receding faster than the speed of light. No signal from those galaxies will ever reach us. They are gone from our observable universe, not through destruction but through the geometry of expanding space. Over cosmic timescales, billions of years, the accelerating expansion will push more and more galaxies beyond our event horizon. The observable universe will shrink, the cosmic web of galaxies will thin, stars will burn out, and in the extraordinarily distant future, a civilization arising in what we might call the lonely era of the universe will look out into a cosmos that appears, to all observational evidence, to consist of only their own galaxy, with no evidence of the vast cosmic structure we can see today. Now, why does this matter to our story about Proxima Centauri? Because it means that the window for exploration, not just interstellar but intergalactic, is not infinite. The universe is not a static stage waiting patiently for us to develop the technology to traverse it. It is an active, evolving system, and it is becoming progressively less accessible over time. Cosmologist Lawrence Krauss and others have argued that we live at what might be called a privileged moment in cosmic history, a time when the universe is old enough for stars like our Sun to have formed and for complex life to have evolved, but young enough that the cosmic structure is still observable, still reachable in principle, still full of other galaxies whose light has had time to reach us. Future civilizations, if any exist in the cosmologically distant future, will inherit a universe that is darker, emptier, and more isolated than ours. They will have less to explore, less to discover, less context for understanding their own origins. They will look at a sky with fewer stars and no external galaxies, and they will have no way of knowing what they have already lost. We are here at the right moment. We are conscious during the universe's most complex and information-rich era, and the stars that are reachable now, including Proxima Centauri, will not necessarily be reachable forever, not because they will move away dramatically on human timescales. On the scale of thousands or even millions of years, the positions of nearby stars relative to Earth do not change dramatically due to cosmic expansion. The local group of galaxies is gravitationally bound and will not be torn apart by dark energy. But the broader point stands. The universe is not waiting for us. The cosmos is on its own schedule, and there is something both humbling and urgently motivating about that fact. There is a concept in philosophy called the overview effect, a term coined to describe the cognitive and emotional shift reported by astronauts when they first see Earth from space. From orbit, the planet appears small, fragile, luminously beautiful against the black. National borders are invisible. The atmosphere, the thin blue line that contains every breath every human being has ever taken, looks heartbreakingly delicate. Astronauts describe a sudden, overwhelming sense of the interconnectedness of all life on Earth and a visceral understanding that we are all, together, crew members of the same fragile vessel. Edgar Mitchell, the Apollo 14 astronaut who walked on the Moon in 1971, described his return journey from the lunar surface in terms that have stayed with me since I first read them. Looking out the window at the stars and at Earth hanging in the darkness, he experienced what he called an instant global consciousness, a feeling as clear and certain as any he had ever known, that the universe was in some sense alive with meaning and awareness. He spent the rest of his life trying to understand and articulate that moment. Now imagine the version of the overview effect experienced by a crew member aboard a ship 1 light-year from Earth, 2 light-years, 4, the sun reduced to a bright star, distinctive, familiar if you know where to look, but no longer the overwhelming presence that has dominated every sky our species has ever seen. Earth invisible, somewhere in the glare of that distant star. Everyone you have ever known, everyone who has ever lived, condensed into a point of light. What does that do to the mind? What does it do to the soul? I think it does something that we do not yet have adequate language for, something that is simultaneously terrifying and transcendent, something that might, in ways we cannot predict, change the people who experience it in ways as profound as the biological changes we discussed in earlier sections. Not damage, transformation. A perspective so vast that the ordinary human concerns that structure everyday life, ambition, status, the small frictions of social existence, simply fall away, replaced by something quieter and larger. Some researchers who study the psychology of extreme environments have speculated that this kind of radical perspective shift, what they sometimes call cognitive expansion, might actually be one of the most important psychological resources available to an interstellar crew, a genuine embodied understanding of their own smallness in the cosmos, combined with an equally genuine, embodied understanding of the extraordinary improbability and preciousness of their own consciousness. This combination might produce a kind of psychological resilience that no amount of training or pharmacology could replicate. The universe, experienced directly and honestly at interstellar scales, might be its own countermeasure, its own medicine. And that brings me to something I want to say directly to you, not about Proxima Centauri, not about physics or biology or engineering, about us. About right now, we are made of the same atoms that were forged in the first minutes after the Big Bang. Hydrogen and helium, the simplest elements in existence. The heavier elements in our bodies, the carbon in our cells, the iron in our blood, the calcium in our bones, were synthesized in the nuclear furnaces of stars that lived and died before our sun was born, scattered across space by supernova explosions, gathered by gravity into the cloud that eventually collapsed to form our solar system. We are, in the most literal and scientifically precise sense, made of stardust, and now that stardust is looking up at the stars and asking, can we go back? That question, in all its audacity, all its terror, all its beauty, is one of the most remarkable things happening in the universe right now, as far as we know. A temporary arrangement of atoms, shaped by billions of years of evolution, sitting on a small rocky world around an ordinary star, wondering whether it can cross the void to visit another star, not because it has to, not for survival, but because it is curious, because it wonders, because something deep in the architecture of consciousness, the same something that drove our ancestors to climb the next hill, to sail beyond the visible horizon, to look up at the moon and dare to imagine standing on it, will not let it rest. That is who we are. That is what we are doing. And the journey to Proxima Centauri, with all of its biological terror, its psychological darkness, its radiation and its isolation and its time-bending physics is simply the next expression of that ancient, irrepressible impulse. Let me tell you about a debate that has been quietly intensifying in the halls of astrobiology departments, philosophy faculties, and space ethics research centers for the last 2 decades. A debate that most popular science coverage skips entirely because it is uncomfortable and because it does not have a clean resolution. But I think it is one of the most important conversations our species needs to have before we send anything, probe or person, to another star system. The debate goes like this. If we arrive at Proxima Centauri b and we find life, even microbial life, even the faintest, most primitive biological signal in a tide pool on the terminator line of that strange, tidally locked world, what do we do? Do we land? Do we stay? Do we build? Do we terraform? Do we treat this other world as a resource for human expansion, or as something with its own integrity, its own story, its own right to exist on its own terms? And if we have already landed before we know, if our boots are already on the ground, our microbes already dispersing into an alien biosphere, before we realize what we have stumbled into, then what? These are not hypothetical questions in the distant future sense. They are questions we need to answer now before we design the mission. Because the decisions we make in the design phase, the protocols we build in or fail to build in, will determine what happens when the moment of contact actually comes. And once a crew is standing on the surface of Proxima b, 4 light-years from Earth with an 8-year communication round trip, there is no calling home for guidance in any practical sense. They will have to decide for themselves, and the framework they bring with them will be the only one available. Let's start with what we actually know about the possibility of life at Proxima Centauri b, because I want to be honest with you about where the science currently stands, without either overclaiming or dismissively ruling things out. The honest answer is that we do not know whether Proxima b can support life. We have discussed the challenges, the flare radiation, the potential atmospheric erosion, the tidal locking, the uncertainty about magnetic field strength. Each of these represents a genuine obstacle to habitability as we understand it from Earth's example. But here is the thing about life that I find endlessly humbling. It is far more resourceful than our intuitions suggest. Consider the organisms we call extremophiles, life forms discovered right here on Earth, in environments that were considered sterile and inhospitable until we actually looked. Tardigrades, microscopic animals sometimes called water bears, can survive exposure to the vacuum of space, to temperatures ranging from nearly absolute zero to well above the boiling point of water, to radiation doses hundreds of times higher than what would kill a human being. They do this by entering a state called cryptobiosis, essentially pausing all biological activity until conditions improve. They have been found in hot springs, in Antarctic ice, in the driest deserts on Earth, on the rooftops of buildings in cities, in the sediment of deep ocean trenches. Chemolithotrophic bacteria, organisms that derive energy not from sunlight but from chemical reactions involving minerals, have been found living in solid rock kilometers below Earth's surface in environments with no light, no oxygen, and no organic nutrients from the surface world. These organisms exist in what is effectively geological time, dividing perhaps once every 1,000 years, living in a world utterly alien to anything visible on the surface. Radio-resistant organisms like Deinococcus radiodurans, which we discussed in the context of genetic modification in Part 4, thrive in environments of intense radiation that would obliterate most life. Acidophiles live in pools of sulfuric acid. Alkaliphiles thrive in solutions so basic they would burn your skin. Psychrophiles are perfectly comfortable in temperatures well below zero. Thermophiles live in hydrothermal vents where temperatures exceed 300 degrees Celsius. Life, in other words, does not read our textbooks about what is supposed to be possible. It finds a way. It exploits every thermodynamic gradient, every chemical disequilibrium, every crack in the rock, and every pool of liquid, and every beam of radiation that carries usable energy. And it has been doing so on this planet for approximately 3.8 billion years, across conditions that have varied enormously over geological time. So when we look at Proxima b, tidally locked, flare-blasted, atmospherically uncertain, and say that it seems hostile to life, we need to hold that assessment with appropriate humility. We are pattern matching against a sample size of 1. Earth is the only world we know with certainty has harbored life, and Earth itself, for much of its early history, would have looked deeply inhospitable by the standards of the life that now covers it. There is a region of particular interest on any tidally locked world, one that astrobiologists have been thinking about carefully. It is the deep subsurface. If Proxima b has liquid water anywhere, and the modeling is genuinely uncertain on this, it may be most likely to exist not on the surface, where the radiation environment is severe and the temperature extremes between day and night hemispheres are dramatic, but underground. A few kilometers below the surface, insulated from the stellar environment above, warmed by the planet's own internal heat, liquid water could potentially persist in environments similar to the deep subsurface aquifers here on Earth, environments we now know host rich microbial communities. This is not wishful thinking. It is a direct extrapolation of what we have learned about life on our own planet, applied to the physical conditions that planetary science predicts for a world like Proxima b. And it has a profound implication for the ethics of arrival. If life on Proxima b, if it exists, is most likely to be found underground, then a surface landing, however carefully executed, might not immediately threaten it. The contamination risk, while real, might be less acute than if life were carpeting the surface. This buys time. It buys the possibility of careful, staged exploration, robotic first, then human, with progressively more invasive investigation only after each stage has been analyzed. But it also means that confirming or ruling out life on Proxima b might require drilling, and drilling raises its own contamination concerns. Every borehole is a potential conduit between the surface contamination we bring with us and the pristine subsurface environment we are trying to study. The history of planetary protection, the international framework governing biological contamination of other worlds, shows how seriously this concern is taken even for Mars, which is far closer and far better studied. For Proxima b, the stakes are even higher because any life there is far more isolated from Earth biology, potentially far more evolutionarily divergent, and therefore potentially far more scientifically precious. Now I want to bring in the voice of someone whose work I think belongs in this conversation and whose perspective is not heard nearly often enough in popular discussions of space exploration. The philosopher and bioethicist Holmes Rolston III has spent decades developing what he calls an environmental ethics of the cosmos, an argument that the moral consideration we extend to living things on Earth should not stop at our atmosphere. That life, wherever it exists, has intrinsic value, not just instrumental value to us, not just scientific interest, but a kind of worth that exists independent of what we think of it or what we can learn from it. Rolston argues that the emergence of life from non-living chemistry is the single most extraordinary event we know of in the history of the universe, that anywhere it has happened, on Earth, potentially on Proxima b, potentially elsewhere, it represents something so improbable and so significant that it demands a form of respect that goes beyond the pragmatic. He is not making a religious argument. He is making a philosophical one, rooted in the observation that the universe has been producing entropy for 13.8 billion years, and that life, complex, information storing, self-replicating, evolving life, is one of the few processes in the known cosmos that locally and temporarily pushes back against that entropic flow. If you accept that framing, then the discovery of life on another world is not just a scientific milestone. It is a moral event. It changes the ethical landscape of the universe in a way that cannot be undone. And our response to it, what we choose to do in the moments after discovery, will say more about what kind of civilization we are than almost any other choice we will ever make. But let's complicate the picture further, because the ethics of arrival are not just about what we might find. They are also about what we bring. Every human being is a walking ecosystem. Your body contains approximately 38 trillion bacteria, outnumbering your human cells by a ratio that researchers are still debating, but which sits roughly around 1:1. Your gut microbiome alone contains somewhere between 500 and 1,000 distinct microbial species, collectively encoding more genetic information than your human genome. Your skin, your respiratory tract, your eyes, all teeming with microbial communities that have co-evolved with our species over millions of years. Every surface a human being touches, every breath a human being exhales, every cell a human being sheds, each one carries this vast community of microorganisms into the surrounding environment. On Earth, this is unremarkable. Our microbiome is adapted to the Earth biosphere and functions as a part of it. But on an alien world, on Proxima b, whose biology, if any, would have evolved in total isolation from Earth life for billions of years, the introduction of Earth microorganisms could be catastrophic, not through malice, not through carelessness necessarily, simply through the unavoidable biological fact of what we are. This is why planetary protection protocols exist. COSPAR, the Committee on Space Research, maintains an international framework that assigns contamination risk categories to different types of space missions and specifies the sterilization standards required for each. Mars, because of its perceived potential for past or present life, is currently classified at the higher end of this scale, requiring significant sterilization measures for any probe that lands there. A mission to Proxima b would presumably demand the most stringent protocols ever developed, sterilization standards orders of magnitude beyond anything currently in practice. But here is the hard truth. Perfect sterilization of a crewed spacecraft is probably impossible. A robotic probe can be baked, irradiated, and chemically treated until its biological contamination load is reduced to near zero. A human being cannot. We cannot sterilize ourselves without killing ourselves. We are the contamination. This creates a philosophical knot at the heart of any crewed mission to a potentially living world. The very thing that makes the mission meaningful, the presence of conscious, wondering, deeply curious human beings, is also the thing that most threatens the integrity of what they find. We are simultaneously the best instrument for exploring an alien world and the worst possible one for preserving its pristine state. Some researchers have proposed that the solution is a strict zoning approach, designating certain regions of Proxima b as permanently off-limits to human presence, accessible only to robotic instruments. Others have argued that the only ethical first mission is an entirely robotic one, with human presence deferred until the biological situation is fully understood, which might mean decades of robotic exploration before any human sets foot on the surface. Still others argue that the very concept of pristine preservation is complicated by the fact that any sufficiently advanced robotic probe also carries some biological contamination risk, and that the line between robotic and human exploration is therefore less morally sharp than it might appear. There are no clean answers here, but the questions themselves are ones we need to be asking loudly, publicly, and with genuine intellectual honesty before the technology makes the decision for us. Now I want to pull back to the very widest view. because everything we have talked about in this video, the biology, the psychology, the physics, the ethics, exists within a context that I think is the most important of all, a context that transforms every challenge and every fear we have discussed into something else, something I would describe as sacred, though I use that word in a completely secular sense. We are, as far as we know, the only species in the observable universe that is consciously asking these questions. I want to dwell on that for a moment, because I think we rush past it too quickly. In a cosmos containing somewhere between 200 billion trillion and 2 sextillion stars, the range of estimates from various large-scale surveys using data from missions like the Hubble Space Telescope and the European Space Agency's Gaia satellite, on a small rocky world orbiting one of those ordinary stars, a collection of atoms has organized itself into something capable of doing what you are doing right now, wandering, asking, reaching outward with curiosity toward the unknown. The universe has been around for 13.8 billion years. For most of that time, as far as we can tell, there was no one to notice it, no one to look at a spiral galaxy and feel awe, no one to measure the speed of light or map the cosmic microwave background or calculate the distance to Proxima Centauri. The universe existed, expanding, cooling, forming structures in complete indifference to its own existence. And then, very recently, in the last blink of cosmic time, something happened. Chemistry became biology, biology became complexity, complexity became consciousness. And consciousness looked up. The astrophysicist Neil deGrasse Tyson has said that we are the universe contemplating itself. Carl Sagan said, "We are a way for the cosmos to know itself." These are not just poetic sentiments. They point to something genuinely extraordinary about the situation we find ourselves in. We are, if we are the only ones, and we do not know whether we are, the universe's only current mechanism for self-reflection, the only way the cosmos has of knowing that it is beautiful. That is an extraordinary responsibility, and it gives every question we have explored in this video a weight that goes beyond the merely practical. Because if we go to Proxima Centauri, if we somehow solve the radiation problem and the psychological problem and the propulsion problem and the ethical problem, we will not just be expanding the range of human civilization. We will be expanding the range of consciousness in the universe. We will be carrying the universe's capacity for self-awareness 4.24 light-years further than it has ever reached. And if we find life there, if Proxima b turns out to harbor its own biology, its own chemistry of self-replication and evolution, then we will be discovering that the universe's capacity for producing awareness is not singular, that life is not a cosmic accident but a cosmic habit, that the question, are we alone? Perhaps the deepest question our species has ever asked, has an answer. The implications of that discovery would dwarf anything else in the history of human knowledge. Every scientific revolution, Copernican heliocentrism, Darwinian evolution, quantum mechanics, general relativity, would be contextualized and in some sense superseded by the single, shattering fact that life arose independently in two places within 4 light-years of each other. The statistical implications alone would transform our understanding of the prevalence of life in the cosmos. If life arose twice in the nearest stellar neighborhood, the inference that it is common, perhaps ubiquitous, across the galaxy would be nearly inescapable. And if we find nothing, if Proxima b is geologically active and chemically interesting but biologically silent, that too would be a profound result. It would sharpen the mystery of why Earth, in this particular neighborhood of this particular galaxy, produced the astonishing diversity of life it has. It would make our own existence feel simultaneously more improbable and more precious. Either way, we learn something fundamental about the nature of the universe and our place within it. Either way, the journey is worth the terror. There is one more dimension of this story I want to bring in before we move toward the final sections of this video. A dimension that sits at the intersection of cosmology and philosophy, and that I think deserves much more public attention than it currently receives. It is the question of what happens to consciousness in the long-term future of the universe. We live, as I mentioned in Part 6, at a cosmologically privileged moment. Stars are burning. Galaxies are still relatively close to each other. The universe is warm enough and complex enough to support chemistry, biology, and minds. But this is not permanent. In approximately 5 billion years, our sun will exhaust its hydrogen fuel, expand into a red giant, and eventually die, taking the inner solar system, including Earth, with it in the process. Long before that, in about 1 billion years, as the sun gradually brightens, the oceans may begin to evaporate, and Earth's surface may become too hot for complex life. In approximately 100 trillion years, one followed by 14 zeros, the last stars in the universe will burn out. The era of star formation, which has been ongoing for 13.8 billion years already, will simply end. The universe will enter what cosmologists call the degenerate era, a vast cold darkness populated by stellar remnants. White dwarfs, neutron stars, black holes. In the extraordinarily distant future, even those remnants will fade or evaporate. Black holes will eventually evaporate through Hawking radiation, a quantum mechanical process predicted by Stephen Hawking on timescales of 10 to the power of 67 years or more for stellar mass black holes, and vastly longer for supermassive ones. Eventually, on timescales so vast, they dwarf the current age of the universe by factors that make the mind go blank. Even protons may decay, dissolving the last solid structures in the cosmos into a thin, cold soup of elementary particles. The universe is mortal, not on any timescale that matters to us personally, or even to our species. But in the ultimate accounting, the stars go out, and the question that haunts some cosmologists and philosophers is this: what happens to consciousness? What happens to the capacity for wonder and understanding and love that has somehow emerged from the cooling embers of the Big Bang in this brief, brilliant, improbable moment? Some thinkers, including the physicist Freeman Dyson, in his famous paper Time Without End, published in 1979, have speculated that consciousness might find ways to persist even in the cooling universe, adapted to ever lower energy environments, thinking ever more slowly as the universe cools, but thinking nonetheless, stretched across cosmic time in a way that preserves the continuity of awareness indefinitely. It is a speculative idea, and subsequent physics has complicated some of Dyson's assumptions. But the impulse behind it feels deeply human, the refusal to accept that awareness, having finally emerged in the universe, must necessarily end. Others take a starker view: the universe will end, consciousness will end with it, and the task of any civilization, aware of this fact, is not to prevent the inevitable, but to make the most extraordinary possible use of the finite time available, to explore, to understand, to experience, to create meaning in full knowledge of its impermanence. I find both of these perspectives beautiful in different ways, and I think the journey to Proxima Centauri belongs to both of them simultaneously. It is an act of defiance against limitation, and it is an act of gratitude for the astonishing, improbable, cosmically brief gift of being aware. We have covered so much ground in this video: the biology of what the journey would do to the human body, the neuroscience of what cosmic radiation would do to the brain, the psychology of isolation so profound it has no historical precedent, the physics of time dilation and the engineering challenges of relativistic propulsion, the uncertain, tantalizing science of Proxima Centauri b, what we know, what we do not know, and what we might find, the ethics of arrival on a world that may have its own story already in progress, and the largest possible view, the cosmic context that gives all of this its deepest meaning. But there are still questions we have not fully addressed. Questions that are, in some ways, the most practical and immediate of all. What would the crew actually look like? How would they be selected? How would they be prepared, not just physically, not just psychologically, but philosophically? What qualities of mind and character would make a human being genuinely suited for the most extreme journey our species has ever contemplated? And what would they carry with them? Not just equipment and food and medicine. What would they carry of us, of human culture, human memory, human meaning, across those 4.24 light-years of void? Those are the questions I will answer now. There is a question that I think most people, when they imagine an interstellar mission, answer too quickly. They picture astronauts, highly trained, physically exceptional, technically brilliant professionals selected through brutal competitive processes for their ability to perform under pressure. Fighter pilots, engineers, scientists, people who have already demonstrated that they can function at the absolute limit of human capability in high-stakes environments. And yes, those qualities matter. Of course they do. Technical competence, physical resilience, the ability to perform complex tasks under conditions of extreme stress, these are not optional on a 20-year journey through interstellar space. They are table stakes. But here is what the research on isolated and confined environments has taught us, slowly, sometimes painfully, over decades of Antarctic expeditions and submarine deployments and space station missions and psychological simulations, about what actually determines whether a person not just survives but genuinely thrives in conditions of radical isolation. It is not what most people expect. And the gap between what we intuitively believe makes someone suited for this kind of mission and what the data actually shows is one of the most important and underappreciated findings in the entire field of space human factors research. Let's start with what does not work, because understanding the failures is as illuminating as understanding the successes. For most of the early history of human spaceflight, crew selection was dominated by a model borrowed directly from military aviation, the right stuff paradigm, immortalized by Tom Wolfe in his 1979 book of the same name. The ideal astronaut was conceived as a paragon of individual competence and emotional control, someone who performed superbly under pressure, who kept their feelings tightly managed, who projected confidence and certainty, who did not burden their colleagues with vulnerability or doubt. Someone, in essence, who seemed not to need anyone. This model worked reasonably well for short missions. Mercury, Gemini, Apollo. These were brief, intensely focused operations demanding extraordinary individual performance over days or weeks. The right stuff model produced remarkable people who did remarkable things under extraordinary pressure. But as missions extended, as the space station era introduced months-long stays in confined quarters with small crews, the limitations of the model began to show. What makes someone an exceptional short-duration performer is not necessarily what makes them an exceptional long-duration crew member, and in some cases, the very qualities that define high individual performance, competitiveness, self-sufficiency, a strong drive for personal achievement, a tendency to internalize and suppress emotional responses, become liabilities when you are sharing a small metal tube with the same 5 people for a year or more. The most comprehensive long-term study of crew dynamics in isolated and confined environments is probably the work conducted by Lawrence Palinkas and his colleagues across multiple decades of Antarctic winter-over research. What Palinkas found, consistently and across multiple cohorts and multiple research stations, was that the psychological characteristic most predictive of positive group outcomes in long-duration isolation was not competence, because the baseline competence of selected individuals was already high. It was not physical toughness, It was not even stress resilience in the traditional sense. It was emotional expressivity, the willingness and ability to communicate openly about internal emotional states. To say, "I am struggling today," or "that interaction bothered me," or "I am feeling disconnected from the group," in ways that invited genuine response and preserved interpersonal transparency. People who could do this without either suppressing everything or flooding the group with unmanaged emotional output turned out to be the anchors of group psychological health in isolated environments. They kept the social fabric of the group intact in ways that high-performing, emotionally contained individuals often could not. This finding has significant implications for how we think about crew selection for an interstellar mission. The person who seems most obviously suited for the journey, the one who appears unshakable, self-contained, effortlessly competent, may actually be the one most likely to generate, over 20 years, the kind of slow, invisible interpersonal damage that eventually fractures a group beyond repair. While the person who seems, by the old metrics, slightly too open, slightly too communicative about their inner life, might be exactly the kind of social glue that holds a group together across 2 decades in the void. There is a related finding from submarine research that I find equally striking. Studies of long-duration submarine crews, which share many psychological features with spaceflight, including confined spaces, limited external communication, high technical demands, and the necessity of maintaining effective teamwork under conditions of genuine physical danger, have consistently identified what researchers call social intelligence as a primary predictor of individual and group performance over time. Social intelligence in this context means something quite specific. It is not charm, it is not popularity. It is the capacity to accurately read the emotional and psychological states of the people around you, to notice, without being told, when a colleague is struggling, when a group dynamic is beginning to deteriorate, when a conflict that has not yet surfaced in words is already running beneath the surface of interactions, and then to do something useful with that perception, to respond in ways that address the underlying issue rather than the surface symptom. This is a skill that can be developed, at least partially, through training and experience. But research also suggests it has significant individual variation that is not entirely trainable, that some people are simply more naturally attuned to the emotional landscape of the groups they inhabit than others. Identifying and selecting for this quality in a rigorous and systematic way would be a significant departure from traditional astronaut selection criteria, but for an interstellar mission, it may be the single most important capability a crew member can possess. Beyond emotional expressivity and social intelligence, researchers studying extreme environment psychology have identified several other characteristics that consistently predict positive outcomes in long-duration isolated settings. The first is what psychologists call cognitive flexibility, the ability to shift between different ways of thinking about a problem, to abandon approaches that are not working without excessive attachment to them, to generate genuinely novel solutions rather than defaulting to familiar patterns. In an environment where unprecedented situations arise regularly, where the crew faces problems that no training scenario has ever covered, because the training scenarios were designed by people on Earth who cannot fully anticipate what a 20-year interstellar journey will actually produce. Cognitive flexibility is not a luxury. It is a survival tool. The second is what researchers sometimes call tolerance for ambiguity, the psychological capacity to function effectively in the absence of clear answers and definitive knowledge. Some people find uncertainty genuinely distressing. Their cognitive systems are organized around the need to resolve open questions, to reach conclusions, to establish certainty. Others can hold open questions comfortably, moving forward and making decisions in the absence of complete information without the anxiety of incompleteness disrupting their functioning. In a mission environment defined by uncertainty about the destination, about the crew's own biological status over time, about the state of Earth, about what they will find, tolerance for ambiguity is essential. The third is a quality that does not have a perfect single name, but which I would describe as purposive meaning-making. The ability to construct and maintain a compelling personal narrative about why the mission matters and why the individual's participation in it is genuinely significant. Viktor Frankl, whose work I mentioned in Part 3, identified this as the core psychological resource of survival in the most extreme circumstances he personally witnessed, the Nazi concentration camps. The people who survived, he observed, were often not the physically strongest or even the most practically resourceful. They were the ones who maintained a reason to survive, a story about why their continued existence mattered. For an interstellar crew, the mission itself provides an obvious candidate for that narrative. You are the first human beings to travel to another star. The significance of that, if fully felt and fully owned, is almost beyond articulation. But significance alone may not be enough to sustain 20 years of daily psychological health. The individual also needs personal sources of meaning, relationships that feel alive and growing within the crew, creative or intellectual projects that engage genuine passion, a relationship with the physical and conceptual world of the mission that generates moments of beauty and discovery amid the grinding routine of survival. Engineering those conditions, designing a mission environment in which meaning is genuinely available rather than just theoretically present, is one of the most underappreciated design challenges of human interstellar travel. And it is one that purely technical people often miss because it looks, from the outside, like a soft problem. It is not. It is as hard and as consequential as any engineering challenge on the mission. Now, I want to talk about something that very few discussions of interstellar crew selection address directly, even though it sits right at the heart of the practical reality. The question of how the crew is assembled, not just who, but together, as a social unit, as a group that must function under conditions of unparalleled stress and isolation, not merely as a collection of highly qualified individuals, but as something greater than the sum of its parts. The research on group composition in isolated environments suggests that diversity of personality type, of cognitive style, of cultural background, of gender, is generally associated with better group outcomes over long durations, provided the diversity is accompanied by genuine mutual understanding and a shared commitment to the group's functioning. Homogeneous groups tend to develop blind spots. They miss perspectives that people with different backgrounds and cognitive styles would naturally supply. They can enter what social psychologists call groupthink, a state of excessive consensus, where the desire for group harmony suppresses individual dissent and critical thinking, with potentially catastrophic consequences for decision-making quality. A crew bound for Proxima Centauri would ideally represent something of the full cognitive and cultural range of human diversity, not as a symbolic gesture, but as a functional strategy. Different people see different things. Different cultural traditions have developed different approaches to the central psychological challenges of isolation, community, meaning-making, and mortality. A crew that can draw on all of those resources is richer and more resilient than one that cannot, but diversity without genuine cohesion is its own risk. A group that is cognitively varied but lacks a shared foundation of mutual trust, shared values, and common purpose can fracture under pressure just as quickly as a homogeneous group. The challenge of crew selection and preparation is therefore not simply to identify the best individuals and assemble them. It is to build, over years of training and shared experience before launch, a social organism that is genuinely capable of self-regulating its own psychological health across 2 decades of the most demanding conditions our species has ever faced. Some researchers have proposed that the training period for an interstellar crew should itself be measured in decades, that the group should live together, work together, navigate conflict and reconciliation together, grieve together, celebrate together, for long enough that by the time they step aboard the ship, they are not a group of strangers who have passed a battery of psychological tests. They are a community with a shared history, a chosen family, the only kind of social foundation strong enough to bear what the journey demands. And then there is the question of what they carry, not physically, though that too is a fascinating design challenge, but culturally, intellectually, spiritually, in the broadest possible sense of that word. What does a crew of human beings bring with them when they leave behind everything that has ever defined what it means to be human? What do you take when you can only take so much of the accumulated meaning and beauty and knowledge of our civilization? This question has been thought about seriously. In 2012, the Arch Mission Foundation was established with the explicit goal of creating what it calls a backup of planet Earth, a record of human knowledge, culture, and biology that could survive catastrophic loss of the civilization that produced it. The Foundation has sent payloads containing encoded human genetic information, the Wikipedia database, and thousands of books to the Moon, to a Tesla Roadster floating in space aboard SpaceX's Falcon Heavy test launch, and to other locations. The Long Now Foundation has been thinking about the preservation of human knowledge and culture across timescales of 10,000 years or more. But for an interstellar crew, the question of what to carry is not primarily about archival. It is about sustenance. What do you bring not to preserve human civilization for posterity, but to nourish the human beings making the journey? What music, what literature, what art, what philosophical traditions, what religious or spiritual practices? Because regardless of one's personal metaphysical commitments, the rituals and frameworks through which human beings have historically confronted mortality, isolation, and existential uncertainty are a form of psychological technology with a track record measured in millennia. Some researchers have proposed that the crew should carry not a fixed selection of cultural content, but a living cultural practice, the capacity to create, to generate new art and music and story in response to their unique and unprecedented experience. A crew that can compose music in the void, that can write poetry about the strange, bruised sky of a tidally locked world, that can paint the light of a red dwarf rising over an alien horizon. That crew is carrying human culture not as an archive, but as a living process. Not the fruit of human creativity, but the root. This feels right to me. And it connects to something that I think is the deepest truth about what the journey to Proxima Centauri actually is. Not just as a scientific mission or a technological achievement, but as a human event. The great Antarctic explorer Ernest Shackleton, whose endurance expedition of 1914 to 1916 remains one of the most extraordinary survival stories in human history, is sometimes quoted as having placed an advertisement in a London newspaper seeking crew members for his Antarctic voyage. The advertisement supposedly read, "Men wanted for hazardous journey, low wages, bitter cold, long months of complete darkness, constant danger, safe return doubtful, honor and recognition in case of success." Historians debate whether this advertisement was real or apocryphal, but the spirit of it is exactly right. And the fact that Shackleton received, by some accounts, over 5,000 responses to it, that thousands of human beings read those words and said, "Yes, I want to go," tells us something profound about what we are. We are creatures who, when confronted with the full honest picture of a journey into the unknown, the cold, the darkness, the danger, the doubt, do not universally turn away. Some of us lean forward. Some of us feel not dread but a rising pull toward the horizon. Some of us are built in some deep and not entirely explicable way for the going. The crew of the first interstellar mission will be those people, not the ones who are fearless. There is no such thing as fearless, and fearlessness, if it existed, would be a cognitive impairment rather than a virtue. But the ones for whom the fear and the call exist simultaneously in roughly equal measure, and who have learned, through training, through self-knowledge, through years of living with both, to walk forward into the fear without being consumed by it. These people exist among us right now. We do not yet have the mission to send them on, but somewhere on this planet, living ordinary lives, going to work and cooking dinner and looking up at the night sky with a feeling they cannot quite name, they are waiting. And what about the rest of us? Those of us who will never go, those of us who will stay on Earth, aging at the normal pace, watching the ship become a fading point of light in the telescope until even that is gone? What do we owe to the ones who leave, and what do they owe to us? I think we owe them honesty, the full, unvarnished truth of what we know and what we do not know about what the journey will demand of them. I think we owe them the best possible preparation, not just technical training, but genuine, deep psychological support across the years of isolation that follow. I think we owe them the sustained, faithful attention of the civilization they left behind. Letters that take 4 years to arrive, yes, but letters nonetheless, proof that they are not forgotten, that the world they gave up everything to represent still knows their names and still values what they are doing, and they owe us something too. They owe us their experience, the full, unfiltered, honest testimony of what the journey is actually like, not the version curated for public relations or scientific reporting, the real version, the loneliness, the beauty, the fear, the moments of unexpected grace, because their experience will be the first data point in a dataset that humanity will be building for centuries. Everything they learn about the body, the mind, the social dynamics of deep isolation, the psychological reality of leaving a world behind, will inform every mission that follows. They are not just travelers, they are the first chapter of a story we are only beginning to write. We are almost at the end of this journey, almost, but not quite, because there is one more question I have been building toward since the very first seconds of this video, one that sits beneath everything we have discussed, like the bedrock beneath a mountain, a question so large and so strange that most science videos avoid it entirely. What if the journey changes not just the people who make it, but us? What if the act of becoming an interstellar species alters something fundamental about what humanity is, not just technologically, not just geographically, but philosophically and spiritually? What if crossing that 4.24 light-year threshold is not just one more step in a long sequence of human achievements, but a genuine threshold, a before and after in the story of consciousness in the universe? There is a moment in the history of life on this planet that I keep coming back to, a moment that happened approximately 375 million years ago in the shallow coastal waters of the late Devonian period, a moment that was not witnessed by anyone, that left no record in any language, that was not celebrated or even noticed, and that nevertheless changed everything. A fish crawled out of the water, not elegantly, not with purpose in any conscious sense, not with any awareness of what it was doing or what it would mean. It crawled or perhaps flopped or dragged itself onto land, driven by whatever combination of evolutionary pressure and biological accident had equipped it with fins strong enough to bear its weight outside the medium it was built for, and it survived, and it reproduced. and 400 million years of vertebrate land life followed from that moment, eventually producing, among other things, the consciousness currently sitting wherever you are sitting, watching this video, wondering about the stars, every bird that has ever flown, every reptile that has ever basked in the sun, every mammal that has ever breathed open air, every human being who has ever lived, every artist, every scientist, every philosopher, every child who has ever looked up at the night sky and felt the pull of the unknown, traces the deepest root of their existence back to that anonymous fish and that anonymous moment on an anonymous shoreline. That fish did not know it was a threshold. It could not have known. Thresholds by their nature are only visible in retrospect, from the far side, looking back. I believe we are approaching a threshold of comparable magnitude, not in 375 million years, not in a million years, perhaps in several hundred years, perhaps sooner if the pace of technological development continues in the directions it is currently moving. And I think the journey to Proxima Centauri, with all of its terror, all of its biological and psychological and ethical complexity, is the first step of the crossing. Let me tell you what I mean when I say threshold species. Because I am using that phrase in a specific and deliberate way throughout the history of life on Earth, there have been what biologists call major evolutionary transitions, moments when the fundamental unit of biological organization changed in a way that opened up entirely new possibilities for complexity and capability. The evolution of the eukaryotic cell, a cell with a nucleus and specialized internal structures, from simpler prokaryotic ancestors. The evolution of multicellularity from single-celled organisms. The evolution of sexual reproduction, which dramatically accelerated the rate of genetic variation and therefore the pace of evolutionary change. The evolution of complex nervous systems and eventually brains. The evolution of language, which allowed the accumulated knowledge of one generation to be transmitted to the next without requiring genetic inheritance, essentially creating a new kind of evolution operating at the speed of culture rather than the speed of DNA. Each of these transitions created a new kind of entity, one that operated according to rules and possibilities that were simply unavailable to the forms that preceded it. A multicellular organism can do things that no single cell can do. A language-using species can accumulate knowledge across generations in ways that no non-linguistic species can. Each transition is genuinely discontinuous, not just a quantitative improvement, but a qualitative leap into a new regime of possibility. The philosopher and complexity theorist Kim Sterelny, among others, has argued that the evolution of cumulative culture in our species represents the most recent of these major evolutionary transitions, the point at which biological evolution was supplemented and in many domains effectively superseded by cultural evolution as the primary driver of change in human capabilities. We are the first species on Earth for which what we know matters more than what we are genetically. The first species whose niche is defined not by anatomy or biochemistry, but by the accumulated, transmissible knowledge we call civilization. And I would argue, carefully, with appropriate uncertainty, that the transition to an interstellar species represents the next such threshold. Not just quantitatively more exploration, more territory, more resources. A qualitative leap into a new regime of possibility, one in which the continuity of consciousness and civilization is no longer contingent on the continued habitability of a single planet, and in which the cognitive and experiential diversity generated by genuinely separate branches of humanity evolving under genuinely different conditions may eventually produce forms of awareness and understanding that are as difficult for us to imagine now as cumulative culture would have been to imagine for a pre-linguistic ancestor. This idea, that the separation of human populations across interstellar distances would, over sufficiently long timescales, produce genuinely divergent forms of humanity is one that I want to explore carefully because it sits at the intersection of biology, philosophy, and deep-time thinking in ways that are genuinely vertiginous. Consider what we know about the divergence of isolated populations on Earth. When a founding population becomes geographically isolated from its parent population, separated by a mountain range, an ocean, a desert, it begins to diverge. Genetic drift alone, in the absence of any directional selection, will cause the two populations to become measurably different over thousands of generations. Add the different selection pressures imposed by different environments, different pathogens, different climates, different food sources, different predators, and the divergence accelerates. Given enough time, the two populations become distinct species, unable to produce fertile offspring with each other, even if they are brought back into contact. On Earth, this process plays out over hundreds of thousands to millions of years, because even geographically isolated populations on the same planet share enough environmental overlap and occasional gene flow to slow divergence. But a colony 4.24 light-years away shares nothing with Earth in terms of environment, no common pathogens, no common food sources, no common gravity, radiation environment, atmospheric composition, or diurnal cycle. No gene flow whatsoever, not a single individual moving between populations after the initial founding voyage. The divergence would be faster, not slower, assisted potentially by deliberate genetic modification of the kind we discussed in Part 4, modifications designed to help the colony survive on Proxima b that would simultaneously make them less like the humans left on Earth, and potentially further accelerated by the psychological and cognitive changes we discussed in Part 2 and 3, the neurological effects of a different radiation environment, of different sensory inputs, of living under a red dwarf sun rather than a yellow one. Give this process 1,000 years. Give it 10,000. Give it 100,000. A blink of an eye in geological time, an eternity in human history. What emerges on Proxima b is not a human colony in any sense we would currently recognize. It is something new, something that started as us and became something else. Not lesser, not greater, but genuinely other. And here is what I find astonishing about that prospect when I let myself really sit with it. The universe would have, for the first time in 4.5 billion years of Earth's history, two separate experiments in the evolution of consciousness running simultaneously in adjacent star systems, comparing notes across the void. Two branches of the same ancient tree, growing in different directions, each illuminating by contrast what the other has become. The scientific and philosophical value of that, the sheer richness of perspective it would generate, is almost incomprehensible. Every question about what is universal in human consciousness and what is contingent, what is written in the deep structure of awareness itself, and what is an artifact of Earth's particular evolutionary history, would suddenly become empirically approachable in ways they never have been before. But I want to ground this cosmic perspective in something more immediate, because the threshold I am describing is not something that happens to our distant descendants in the abstract. It begins with specific choices made by specific people right now about what we value and what we invest in and what kind of future we are trying to build. The development of the technologies required for interstellar travel, propulsion systems capable of reaching meaningful fractions of the speed of light, life support systems capable of sustaining human beings for decades, radiation shielding capable of protecting the brain and DNA from galactic cosmic rays, communication systems capable of bridging light-year distances, Each of these will require sustained investment of scientific and engineering talent and financial resources on a scale comparable to or greater than the Apollo program, not for a decade but for generations. And here is the honest question that sits at the center of that reality. Is it worth it? There are people, thoughtful, serious, morally engaged people, who argue that it is not, that the resources required for interstellar exploration are resources that could address the immediate, present tense suffering of billions of human beings on Earth right now. That clean water and food security and disease prevention and climate adaptation are not less important than reaching the stars, and that the choice to prioritize the distant and speculative over the immediate and concrete is itself a moral statement, and not a flattering one. I take this argument seriously. I do not dismiss it. Anyone who does is not thinking carefully enough about the actual human stakes involved. But I also think the framing of it as a binary, stars or Earth, exploration or justice, is a false one. The technologies developed in pursuit of space exploration have, historically, generated returns far exceeding their cost in terms of practical applications on Earth: satellite communications, GPS navigation, water purification systems, memory foam, scratch-resistant lenses, insulin pumps, CAT scan technology. The list is long and genuinely impressive. The investment in going outward has consistently produced dividends for the people who stayed behind. More fundamentally, I think the question of whether to become an interstellar species is not really a question about resource allocation. It is a question about what kind of species we want to be and what kind of future we want to build. Civilization that chooses to remain permanently bounded by a single solar system, however it uses the resources of that solar system, is making a choice about the ultimate horizon of its ambition and its curiosity. It is saying, in effect, this is enough, we go no further, and everything in the history of our species suggests that this is not, ultimately, who we are. Every horizon we have ever reached has revealed another. Every ocean we have ever crossed has had a far shore. Every summit we have ever climbed has shown us higher peaks. We are not a species that stops, we are a species that continues. There is a concept in the philosophy of science called the cosmic perspective, the view from the largest possible scale, which contextualizes human concerns and human history within the framework of the universe's full four-dimensional extent. It is a perspective that can, if applied carelessly, trivialize human suffering by reducing it to insignificance against the backdrop of cosmic vastness. The universe is vast and old and indifferent, and if you lean too hard on that fact, you can end up somewhere emotionally cold and philosophically useless. But applied with care, with the understanding that the cosmic perspective does not diminish human experience, but contextualizes it, it produces something I find genuinely transformative. It produces the recognition that we are not separate from the universe, looking at it from outside. We are the universe, looking at itself from inside. Our curiosity is cosmic curiosity. Our wonder is the cosmos experiencing wonder at its own existence. Our suffering is real and matters, not because the universe assigns it significance, but because we do, and we are the universe's mechanism for assigning significance to anything. This means that the choice to go to the stars is not a betrayal of our responsibility to each other. It is an expression of the same impulse that generates that responsibility, the impulse to say that existence matters, that awareness is precious, that the story of consciousness in this universe is worth continuing and extending and enriching as far as we can possibly reach. Carl Sagan, whose shadow falls over every serious conversation about space exploration and who I return to again and again because he understood not just the science but the human meaning of it, put it this way in his book Pale Blue Dot, published in 1994. He wrote, "We were hunters and foragers. The frontier was everywhere. We were bounded only by the earth and the ocean and the sky. The open road still softened our souls, beckoned us toward uncharted lands and the allure of the unknown. Long summers, mild winters, rich harvests, plentiful game, none of them could hold us back. Then, amid the slow piling of the generations, the land was filled. The great wandering was over. The age of the frontier was done. Today, every place on Earth has been mapped, settled, or claimed. We have satisfied our ancient hunger for new territories by exploring vicariously through television and film. But if our species is to survive, if we are to find meaning in the universe, if we are to alter the course of history and avert the tragedies that seem to threaten us, then we need to go. We need to go. Not because going is easy or safe or certain. Not because the challenges are manageable or the risks acceptable by any ordinary standard, but because going is what we are. It is the deepest expression of the consciousness that has somehow, improbably, impossibly, emerged from the matter of this universe and turned to look at itself. And now I want to say something about fear, because this entire video has been, in some sense, a catalogue of reasons to be afraid. The radiation, the isolation, the cognitive degradation, the gravitational loss, the psychological fracturing, the ethical weight, the vast, indifferent darkness of 4.24 light-years of vacuum. Every one of those fears is real. I have not exaggerated any of them. The science is clear and the stakes are genuine. But fear and meaning are not opposites. They are at the deepest level of human experience, companions. Every meaningful thing any human being has ever done has been shadowed by fear. Every act of love, because love means vulnerability. Every creative act, because creation means the possibility of failure. Every commitment to something larger than yourself, because commitment means the possibility of loss. The astronauts who flew to the moon were afraid. The sailors who first crossed the Atlantic were afraid. The first human beings who walked out of Africa into unknown territory were afraid. And they went anyway. Fear is not the enemy of courage. It is the precondition of it. You cannot be courageous in the absence of fear. You can only be reckless. The crew of the first interstellar mission will be afraid, and they will go anyway. And in going, they will do something that I believe matters at the deepest level at which anything can matter. They will extend the reach of consciousness in the universe. They will carry the 4-billion-year story of life on this planet across the void to a new shore. They will do what that anonymous fish did 375 million years ago, but with full awareness of what they are doing and full choice in the doing of it. That awareness, that choice, that is what makes it not just biology but meaning. That is what makes it not just travel but transformation. That is what makes it, in the fullest and most honest sense of a word I do not use lightly, sacred. We are in the final stretch now. One more part to go. And in that final part, I want to do something slightly different from what we have been doing. I want to step back from the science and the philosophy and the ethics, all of which we have now laid out as fully and honestly as I know how, and speak directly to you about what you carry away from this, about what the journey to Proxima Centauri means not for the distant future of our species, but for the person watching this video right now, living their life on this small blue world, looking up at the night sky and wondering, because I think there is something here for all of us, not just the ones who might one day make the journey. All of us want to start this final part differently from all the others. No statistics, no scientific studies, no mission names or telescope data or research papers, just a question, a simple one, the kind that sounds almost too simple until you actually sit with it. And then it opens up beneath you like a depth you did not know was there. When was the last time you looked up, not glanced? Not noticed the sky on the way to somewhere else. I mean really looked. Stopped moving, stopped thinking about whatever was next on the list, tilted your head back and let the night sky have your full attention. stayed with it long enough for the scale of it to begin to register. If you live anywhere near a city, the light pollution probably hides most of it. You see a few bright stars, maybe the moon, maybe a planet if you know where to look. But even that partial sky, even that handful of photons fighting through the orange glow of human civilization, is telling you something extraordinary if you are willing to receive it. Every point of light up there is a sun. Most of them are larger than ours. Many of them are older. Almost certainly, statistically, most of them have planets. And the light hitting your eye right now left those stars not tonight, but years ago, decades ago, centuries ago, millennia ago. You are not seeing the stars as they are. You are seeing the past delivered to your retina at the speed of light. The star you are looking at may not even exist anymore. It may have died, exploded, collapsed, cooled to darkness, while that ancient light was still traveling toward you. You are holding a message from something that may be gone. That is not a sad thought, or rather, it is sad and beautiful simultaneously, in the way that only true things can be. It is the sky telling you, in the only language it has, that time is real and vast, and that presence is precious precisely because it does not last. We have spent this entire video exploring why the journey to Proxima Centauri is scarier than most people think. And we have not flinched from that. The radiation is real, the isolation is real, the biological deterioration is real, the ethical weight is real, the physics of time dilation is real. The possibility of arriving and finding nothing, or arriving and finding something so profound it shatters every framework we brought with us, both of those are real. I said at the beginning that I wanted to reframe this story, not as a story about engineering challenges, as extraordinary as those are, but as a story about what it means to be human at the edge of the possible, about the biological and psychological and philosophical evolution required to become the kind of species that can cross interstellar space and survive what that crossing demands. And now, at the end, I want to bring that reframe all the way home, because I think the most important thing this story reveals is not about space. It is about here, about us, about who we already are and what we are already capable of, if we are willing to look at ourselves clearly, consider what the research we have discussed actually shows about the human being, not as an astronaut candidate, not as a crew member of a future interstellar mission, but as the thing you are right now, a biological organism shaped by 4 billion years of evolution, carrying within yourself a set of capabilities and vulnerabilities that are the direct expression of everything life on this planet has learned about surviving and adapting and persisting in the face of conditions that would seem, from the outside, to make survival impossible. Your body is extraordinary. It maintains dozens of precisely regulated systems simultaneously: temperature, blood chemistry, immune response, circadian rhythm, hormonal balance, in the face of constant internal and external perturbation. It heals cuts and repairs broken bones and fights off millions of microbial invaders every day without your conscious awareness or direction. It has been doing this for your entire life, without a single day off, with a reliability that the most sophisticated engineering systems in human history cannot approach. Your brain is more extraordinary still. It contains approximately 86 billion neurons, each forming on average 7,000 synaptic connections with other neurons for a total of roughly 600 trillion synaptic connections, a number so large that if you counted one per second, it would take you longer than the current age of the universe to finish. This network processes sensory information, generates language, constructs models of other minds, simulates possible futures, experiences beauty and grief and curiosity and love, and somehow, in a way that remains one of the deepest unsolved mysteries in all of science, produces the subjective experience of being you. You are, in the most rigorous and literal scientific sense, the most complex known structure in the observable universe, not as a species, you personally, individually, right now, and yet we spend most of our lives entirely unaware of this. We experience ourselves as small, limited, ordinary, bounded by the familiar walls of daily life. We worry about things that, from the perspective of deep time and cosmic scale, are genuinely tiny. We compare ourselves to other people and find ourselves wanting. We feel inadequate and uncertain, and sometimes overwhelmed by the simple mechanics of getting through the day. I do not say this to dismiss those feelings. They are real. The difficulties of ordinary human life are real, and the people living them are not obligated to feel cosmically uplifted at all times. That would be its own kind of distortion, toxic positivity dressed up in the language of astrophysics, but I do want to offer you something. A perspective that I have found genuinely useful, not as a way of escaping the difficulties of ordinary life, but as a way of carrying them differently. A perspective that comes directly from the science we have been discussing throughout this video, the challenges of an interstellar crew, the isolation, the uncertainty, the necessity of maintaining meaning in the face of conditions that systematically undermine it, the requirement to hold yourself together psychologically when everything familiar is gone and nothing about the future is guaranteed. These are extreme versions of challenges that every human being faces in the course of an ordinary life. Isolation. Every person who has ever experienced loneliness, real loneliness, the kind that persists even in crowds, knows something about what an interstellar crew will face. Not the same magnitude, but the same territory, uncertainty. Every person who has ever had to make a major decision without adequate information, who has had to act in the absence of knowing how the story ends, who has had to move forward into a future that offered no guarantees. They know something about the psychological demand of deep space, meaning under pressure. Every person who has ever had to find a reason to keep going when the circumstances of their life were actively working against them, who has had to construct, through sheer force of internal commitment, a narrative about why their existence mattered when the external evidence was not cooperating. They know something about what survival in the void requires. The research on psychological resilience in extreme environments is, at its deepest level, research on what human beings are capable of when the conditions that normally sustain well-being are stripped away. And what it consistently finds is that the core resource, the thing that makes the difference between fracture and growth, is not external, it is internal. It is the capacity to make meaning, to choose a story, to decide, in the face of every pressure that would make surrender rational and reasonable, that the journey is worth the cost of the ticket. Viktor Frankl, writing about his experience in the concentration camps, the most extreme confined and isolated environment a human being has ever been forced to endure, put it with a precision that I have never found improved upon. He wrote, "Everything can be taken from a man but one thing, the last of the human freedoms, to choose one's attitude in any given set of circumstances, to choose one's own way, to choose one's own way. In the void between stars, with no external authority to appeal to, and no rescue coming and nothing guaranteed, that is the only freedom that cannot be taken. And it is, ultimately, the only freedom that matters." Now I want to say something about Proxima Centauri specifically, about that small, dim, angry red star 4.24 light-years away that I think often gets lost in the technical discussions. Proxima Centauri has almost certainly been there, in roughly its current form, for longer than our Sun has existed. It is what astronomers call an M-type red dwarf, the most common type of star in the galaxy, constituting approximately 70% of all stars. It burns so slowly and so coolly that it will remain on the main sequence, fusing hydrogen in its core, for approximately 4 trillion years. Our Sun will live for about 10 billion years total. It is currently about 4.6 billion years old, roughly middle-aged. Proxima Centauri will still be burning, steady and red, when our sun is a cold white dwarf, and the solar system we know is a frozen, lightless ruin. There is something almost unbearably poignant about that to me. The nearest star to our sun is also the most patient, the most enduring, the one that will outlast everything we know by a factor of almost 400. It has been there, burning quietly, for billions of years before the first fish crawled out of the water. It will be burning quietly for trillions of years after the last conscious being in our solar system has drawn its last breath, and Proxima b, that rocky, tidally locked, radiation-battered world circling in the habitable zone of that patient red star, has been there too, waiting, in whatever sense a planet can wait, through more time than the human mind can genuinely process. If there is life there, even the simplest, most primitive form, it has had billions of years to adapt to those conditions, billions of years to find the chemical pathways, the protective strategies, the biological solutions to a radiation environment and a tidal lock and a stellar spectrum that would seem, from Earth's perspective, deeply hostile. Whatever biology Proxima b has produced, if any, is almost certainly utterly unlike anything on Earth. Not because the laws of chemistry are different there. They are not, but because the specific pressures and resources available to evolution on that world are so different from ours that the solutions evolution found there would have diverged from Earth life almost immediately and continued diverging across billions of years of separate history. The thought of meeting that life, even through the indirect evidence of a spectrum or a chemical signature detected by a probe, even without direct contact, is one that I find genuinely vertiginous, not in a frightening way. In the way that standing at the edge of a vast canyon is vertiginous, the dizziness of suddenly perceiving a depth that was invisible until you got close enough to see it. Let me bring all of this together now. Because we have covered an enormous amount of ground in this video, more, I hope, than you expected when you first clicked on it. And I want to make sure you leave with the things that matter most. We have learned that the journey to Proxima Centauri is not primarily a story about distance. Distance is the frame, but the real story is about transformation, about what the journey demands of the human body, the human mind, the human soul, and about whether we have within us, or can develop within us, what the journey requires. We have learned that the biological challenges are severe and real. Microgravity dismantles the cardiovascular system and weakens the bones. Galactic cosmic rays penetrate every known shielding material and damage the DNA and neurons of anyone exposed to them across years or decades. The immune system shifts in directions that research is still working to understand. The eyes suffer from intracranial pressure changes that can impair vision in ways that may be irreversible. These are not hypothetical risks. They are documented, measured, experimentally confirmed consequences of the spaceflight environment. We have learned that the psychological challenges may be even more formidable. Isolation so complete and so prolonged that it has no historical precedent in human experience. Communication delays so long that in any moment of crisis, the crew is on its own in the most absolute possible sense. The slow psychological attrition of years of confinement, the interpersonal friction of forced proximity, the existential weight of a journey from which there is effectively no return. We have learned that the physics of the journey is its own kind of terror and its own kind of beauty. Time dilation, real, confirmed, experimentally verified, means that a crew traveling at high fractions of the speed of light would return to an Earth that has aged faster than they have. The people they left behind would be older, perhaps gone, perhaps replaced by children who were not yet born when the ship launched. The universe itself enforces a kind of loneliness on the interstellar traveler that no amount of psychological preparation can fully address. We have learned that the ethical dimensions of arrival are profound and underappreciated. If Proxima b harbors life, even microbial life, the decisions made in the first hours and days of contact may be the most consequential any human beings have ever made. The crew will be 4 light-years from any external guidance, carrying within their own contaminated bodies the greatest biological threat to any native biology they might encounter. Every protocol they follow or fail to follow will be a moral choice, made in real time with no possibility of appeal, and we have learned that all of this, the terror, the risk, the ethical complexity, the psychological darkness, sits within a context so vast and so beautiful that it transforms the fear into something else. Something I have been trying to name throughout this video, and that I think perhaps cannot be perfectly named, only experienced. The sense that we are part of something so much larger than ourselves, that our individual concerns, real and important as they are held within a story whose scale and grandeur is genuinely incomprehensible. We are made of atoms forged in the first moments of the universe and in the hearts of stars that died before our sun was born. We are the product of 4 billion years of biological evolution on a rocky world around an ordinary star. We are, as far as we know, one of the universe's only current mechanisms for self-awareness and self-reflection, and we are standing at the edge of the solar system, looking outward, wondering whether we can go further. That is who we are, that is what we are doing, and the journey to Proxima Centauri, terrifying as it is, demanding as it is, uncertain as it is the next expression of the oldest and deepest thing about us. There is a phrase in the language of exploration that I have always found quietly extraordinary. When navigators in the age of sail ventured beyond the mapped world, beyond the coastlines and the trade routes and the familiar stars of the northern sky, they used to say they were sailing beyond the edge of the known. Beyond the edge of the known, not beyond the edge of what exists, not beyond the edge of reality, just beyond the edge of what is currently mapped. An acknowledgement that the world continued beyond human knowledge of it, that the darkness on the chart was not absence but unexplored presence, that what was unknown was not therefore non-existent, just waiting. Proxima Centauri is beyond the edge of the known in exactly that sense, not dark, not absent, not nothing, just unmapped, unreached, unexperienced by any human consciousness. A sun burning patiently around which a planet circles, and on that planet, perhaps, chemistry doing what chemistry does in the presence of liquid and energy and time, perhaps organizing itself, perhaps replicating, perhaps, across billions of years of patient experimentation, becoming something we do not know. And the not knowing is not a failure, it is an invitation. Here is what I want you to take from this video. Not the facts, though I hope the facts stay with you because they are remarkable, not the names and the numbers and the scientific findings, though those matter too. What I want you to take is something more fundamental, the qualities that would make a human being capable of surviving and thriving on the journey to Proxima Centauri. Emotional resilience, the ability to make meaning under pressure, social intelligence, cognitive flexibility, the willingness to live with uncertainty, the capacity to find beauty in difficulty. These are not exotic qualities possessed only by future astronauts. They are human qualities. They are your qualities in embryonic or developed form right now. The universe is not a place you are separate from, looking at through a screen. You are inside it. You are made of it. The same physics that governs the behavior of stars governs the atoms in your body. The same chemistry that might be producing life on Proxima b produced the first living cells on Earth 4 billion years ago and has been expressing itself in increasingly complex forms ever since, culminating, at least locally, at least for now, in you. Every time you choose curiosity over fear, You are expressing something that is, in the most literal scientific sense, cosmic. Every time you choose to reach towards something difficult and uncertain and genuinely worth doing, you are doing what life has been doing on this planet for 4 billion years, pushing against entropy, against limitation, against the pull of the familiar and the safe, towards something larger and more complex and more aware. That is not metaphor, that is physics, that is biology, that is the story of everything. Proxima Centauri is 4.24 light-years away. At the speed of the fastest spacecraft we have ever built, it would take approximately 73,000 years to reach. With technology currently on the drawing board, breakthrough starshots, laser-driven light sails, a tiny probe might reach it in 20 years. A crewed mission, at the velocities required for a human lifespan to survive the journey, remains centuries away at best, but the journey has already begun. It began when the first human being looked up at the night sky and felt something. Call it curiosity, call it longing, call it the specific ache of wondering what is out there. It continued through every generation that mapped the stars and measured their distances and looked for planets and asked whether we are alone. It continues right now in every observatory and laboratory and research station and spacecraft currently in operation. In the scientists and engineers and philosophers and ethicists who are laying the intellectual groundwork for a mission that none of them will live to see launch it, and it continues in you, right now, in the fact that you watched this video, in the fact that you wanted to understand not just whether the journey is possible, but what it would demand, what it would cost, and what it would mean and why it would matter. That wanting, that reaching toward understanding, that refusal to look at the universe and be satisfied with not knowing, that is the beginning of every journey that has ever mattered. The stars are not only out there, in the only sense that ultimately matters, they are already inside you. They always have been. Go look up tonight. Really look. Let the scale of it land. Feel the ancient light on your face and know what it is. Know, in the precise and rigorous and extraordinary language of science, that you are a temporary arrangement of stellar material that has become aware of its own existence and is looking back at the source. And know that somewhere out there, 4.24 light-years away, a small red star is burning, patient and ancient and enduring, around a world we have not yet reached. Not yet. You just saw what 4 light-years can do to a human being. But here is the thing, that is the closest star. What happens when you go further? The answer is not just harder, it is genuinely terrifying in ways most people never consider. That video is on your screen right now. Click it. You will not look at the night sky the same way again.